all the medical data is disclosed, but not both. So this is like an either-or policy. And another thing is data structure, like trees, may have multiple policies. I will give some more example later. The last problem is that existing languages usually require programmers to explicitly enforce policies within the program logic. And it gets more complicated when you have complex policies and structured data. This is because you will have to restructure the programs to capture the policies and also make sure the control flow only depends on the public information, which makes the programs harder to read, write, and reason about, makes the policies harder to update and audit, and also makes it harder to support multiple policies. So the bottom line here is basically we want to separate the privacy policies from the application logic. In particular, we want to allow the programmers to write applications independently of the policies and specify and audit the policies independently of the functionality. In other words, we want to have some kind of like policy agnostic approach. And here, I want to allow the programmers to write their functionality as some functional programs with structured data and high order function and all this good stuff, without thinking of policies though. And then they can define their policies separately, and somehow we can compose them and derive a secure version. So this is the goal we are trying to reach. And in fact, we have attempted to bridge all these gaps in our previous work. We have introduced something called oblivious algebraic data types, which is a way to encode structured data type and also their privacy policies, which I will briefly talk about next. And we have also proposed runtime semantics called tape semantics, which is a way to enable the separation of privacy policies and program logic. But in the interest of time, I'm not going to mention these semantics. You can read the paper to learn more about it. In this work, we introduced a language called TapeC, which is extended from the previous work. And it also decouples privacy concerns and the programmatic concerns. But we do it this time by statically enforcing the privacy policies. In particular, we designed an algorithm that basically takes a public program and a desired privacy policies, and we can combine them and generate a secure version that respects the policies and also preserve the behavior of the original program. And we ran some experiments. Our results show that this new static enforcement strategy offers significantly better performance compared to the previous approach. Okay. All right. What we'll be doing now is to give you a quick tour through this very simple example about how this language works at a very high level. So this is a list data type with an integer payload. The definition should be very standard as an algebraic data type. And here we have a filter function with a threshold as an argument and also a list of integers. So basically, this function does is basically just like keep all the numbers in the list that's below the threshold and remove the others. By the way, we do support higher order functions. This is just a simplified example. Okay, now we have a data and also a program. To implement a private version of that, we first need to give them some privacy policies. So what is a policy? In this context, a policy specifies what information can be publicly shared, which can be any arbitrary projection of the data because we want to support complex policies. And we call this publicly shared information public view. And then we can encode a policy for structured data as oblivious algebraic data types, or OADT. I'm not going to talk about the details of how this works because it's not very important for this talk. But we defined an OADT called list head something. The head here doesn't mean anything. The syntax is just a visual cue for security-related stuff. So an OADT is a dependent type, which depends on the public view, which again is the publicly available information that everybody agrees on. And in this case, I choose the maximum length of the list as the public view. So essentially, the policy for this private list is that I want to hide everything except for the maximum length. I can release the maximum length as long as other things are kept secret. And the type body here describes the representation, or you can say the shape, of the private component of the private list. And importantly, this shape is completely determined by the public information, which is the type index. So that the attackers, does the mic working? Okay. So that the attackers cannot infer any private information by looking at how the data is represented. And we also have some oblivious operations to build and manipulate OADTs, but I'm not going to cover those. Okay, here's one example of the previous OADT with the public view 2. So basically, this is a private list with at most 2 elements. Here is one instance of this, this type. It has exactly 2 elements. And here is a list with only 1 element, and here is an empty list. And a key here is the OADTs will automatically pad this private list with dummy secure values so that all the private lists of this same type of this OADT will have the same representation, or you can say they look the same to the attackers. They are indistinguishable regardless of how many elements they actually have and what exactly these elements are. Okay, and of course, revealing the maximum length is just one policy. You can also choose to just disclose the exact length. By doing so, you hide less information, but also you have more succinct data representation and more efficient computation. So here's some trade-off you need to make. Okay, all right. To enable modular translation, in this work, we extended the previous type system with something called site type. So what is a site type? You can build a site type by putting a site before the OADT, but if you know dependent type, it's really just a fancy name that I gave to this variant of dependent sum type. And here is one instance of this type. I use this pair syntax because you know dependent sum type is secretly just a fancy pair. So the first component of this pair is the public view, the publicly known information, and the second component is the secure value, the secure component whose type or shape is indexed by the first component. So basically what we do here is we package the private data with the public view, and by doing so, we effectively hide the dependent types from the end users. And with that, let's say we want to implement a private version of this filter function. All you need to do is just to provide a different type signature, which still has to be compatible with the original type, and we have a more precise definition of compatibility in the paper. But in this case, we want to take a private integer for the threshold, and we want to take a private list which discloses the maximum length and return the same OADT. And the implementation of this function is literally just like calling a meta function called lift on this public filter function. And if you want to use a different policy, you just specify different type signature, and that's it. But of course, it's still possible to specify an invisible policy. And in this case, the type checker will just yell at you. In this last example, if you know the exact length of the input list, it's still impossible, or you can say insecure, to reveal the exact length of the resulting filter of the list, because the threshold and also all the elements in the list are still secure. So, okay. Unfortunately, I'm not going to go into details about how this lifting algorithm works, but at a very high level, the lifting algorithm, that lift keyword, translates a normal standard program to a version of a given type signature, or you can say policy, with some type variables, while generating constraints over these variables. And then we solve the constraints, and finally, we instantiate the type variables with the solutions, and then do some massage on the program to make them better. And this process, as you can tell, is very similar to a type inference algorithm. Okay, so the constraints we generate assert the capability of the types and also the relations on the type. For example, one constraint is if the type have certain structures. And I didn't actually mention about structures, but each OADT is optionally equipped with a set of structures with the methods and also the laws they need to obey. In the paper, we have the mathematical definitions of all these structures, but I'm not going to talk about them here, but these structures are key to the translation algorithm. Okay, in terms of constraint solving, most constraints are lowered to formulas in an efficient logic called quantifier-free finite domain theory. For some other constraints, for example, the function call constraints, which resolve the policies of intermediate function calls, they are handled similarly to a fixed point calculation. So essentially, the constraint solving is just the interplay of these two components. All right. Of course, now we introduce some compilation overhead because we need to do some constraint solving, and we use Z3 for solving the quantifier-free finite domain theory. But fortunately, as you can tell from the table here, the compilation overhead is pretty reasonable, and the lifting algorithm is expressive enough to capture all the case studies from our previous work, and also some new case studies we added to this work. So in terms of performance, I'm not sure if you can see the text there, but it doesn't really matter. The blue bars means the running time of this new approach relative to the old dynamic approach, and the red line there is the baseline. So the blue bar, the shorter of the bar, the better. And there are some green test cases there. Those are the test cases where the previous approach simply just times out or runs out of memory, but the new approach can finish them in seconds. So the takeaway here is basically this new policy enforcement strategy is exponentially better than the previous one in performance for many applications, but work roughly as well for the rest of them. I will quickly gloss over all the formal guarantees. We have formalized the core calculus, and we have a Q-type system, but I didn't have time to talk about it. But we have proved the type soundness property and also a security property called obliviousness, which basically says no private information can be inferred by observing every program state of the execution traces. And we have proved the lifting algorithm always generates secure implementations, and also they always generate correct implementations in the sense of a refinement. So basically what that means is the generated programs preserve the behavior of the original programs. And this refinement is formulated as a step index logical relation. I also show some theorems on the slides, which probably don't make much sense out of context, but I put them there anyway to show you I'm not pulling this claim out of my ass. Okay, and to wrap up, we have this language that supports rich private structured data and complex policy through oblivious algebraic data types. And we have a security type system that makes sure the programs are safe by construction. And we allow the users to easily implement their privacy, secure applications by decoupling the privacy policies from the program logic using this lifting algorithm that statically enforces the privacy policies. And we got theory and also implementation for the type checker and end-to-end compiler for type C that you can play with. And with that, that's pretty much it. Thank you for your attention, and I'm happy to take any questions.
Questions?
It wasn't clear the attacker model. Are you considering timing?
Yes. The timing channel is handled by our security type system. So basically, the formal guarantee we have for the language, the oblivious property, implies a stronger threat model in the sense that not just observing the timing channel, even if you can observe every program state of your program execution, there will not be any information.
All right, so I have following up question then. So because you generate these stars, when you don't have information, you want to create a list of certain size, then you have certain stars, right? Because you might not have the whole information.
Right.
So what is the semantics? When a function hits a star, it still needs to continue computing till the end of the list. And I could imagine that if you are doing a filtering, the way that you compute with a star is in one way. If you do an addition, you need to be constant time in the addition, So because here what you're showing, you have n reduction steps in the semantics, which might not be the same as the timing that you observe in the program. So how you bridge that gap?
So in our formal model, the semantics of the language, we basically keep track of every program state, and we make sure if you have like two indistinguishable programs, in the sense that they only differ in the secure values. They will always kind of execute in this like matching style. And every
I get that, but maybe we can chat offline because maybe I can explain.
No, I think I get your point, but in terms of timing channel, it is subsumed by this model, but I guess there might be some like more subtleties that that's in your mind that probably is better to take it offline.
All right, thanks.
All right, so we have to move on to the next speaker, but thank you again.
Okay, thank you. Oh, right.
So our third speaker in this session is Alex, who's going to be talking to us about gradient, gradual compartmentalization via object capabilities tracked in types. Or hopefully, anyway.
Okay. So yeah, we can't see the presentation. It is on the second screen somehow. Okay. Okay, good. Thank you for the introduction, and let's dive right in. I want to start on a very cheerful note, which is that we have a problem. And the name of the problem is supply chain attacks. So you may have read of examples like Log4Shell or SolarWinds or the XZutils fiasco. So let's talk about, let's see what these are about. So on your computer, you can use Chrome to browse the internet and download some files, which is all very good as long as Chrome does what you want. But Chrome uses third-party libraries. And an attacker could install a backdoor in a library used by Chrome, and in principle, they could gain the exact same access to your computer as Chrome. And if they did that, that would be really bad news, right? So they could steal secrets from your disk, they could read your passwords that you type, and they could do the very same thing to millions of other people. And ultimately, the problem is that it's enough to compromise just a single dependency, and modern applications can have even thousands of them, which happens for JS. An appropriate architecture makes applications much more resistant against such attacks. And we've known this for half a century. So paraphrasing, every part of a program should operate using the least authority necessary to complete the job, right? That's the POLA, that's the principle of least authority. Now, okay, it's just a principle. We also need a pragmatic enforcement mechanism. So one approach is to compartmentalize parts of the program, which is to say we run them in an environment such that accessing anything outside of this environment is completely controlled. So what Chrome does is it runs libraries inside the processes, which you may have seen. So this does the job, but it leaves a lot to be desired, right? Because now you need to communicate between processes. Now you need to express policies in OS-level concepts. And the only way to tell if your policy is too restrictive is to run the program and see if it crashes. So I don't think I need to convince you that things could be better if we did a PL-based approach. And it turns out we do have such an approach. So the object capability model is great here. It's very flexible, as we will see, and it's very natural for people familiar with OOP, which is a lot of people. But so far, it had a particular issue, which is that adopting it required migrating the entire application in a single go. And so what if that didn't need to be the case? What if we could take an existing application and gradually migrate it to using object capabilities, every part by itself? What if we could migrate the ecosystem library by library, and applications could use any library without having to compromise on enforcing security policies? So that's the vision that we have, and to help realize this vision, we developed the gradual compartmentalization approach, and as well as gradient, which is a proposal for a Scala-free extension utilizing the approach. Okay, so now you know what's on sale. So let's motivate object capabilities. So the current status quo is that library code can access whatever system features it wants, right? So here we have some Scala code which uses the log4j Java library. And you know, it might look innocuous, it might just look like it's just logging things, but actually it could be downloading some code from the internet and running it, right? Which is basically what the log4shell vulnerability actually was. And the situation would be a lot better if we were using object capabilities. So the basis of this model is that code starts with no ambient authority. So the access to all system features is only possible by calling methods on capabilities, special objects, and they need to be received from the outside. So what we see here is the same snippet as before, but now it's in gradient, right? Our proposed Scala-free extension. We are using caplog, which is an object capability version of log4j. And now, to create a logger, we first need to instantiate caplog, right? So here, main initializes caplog with capabilities for accessing the file system, network, and evaluating code. Okay, so it's already better because you know that eval thing over there, that's quite fishy. Where do these guys come from? So this code is actually organized into modules. And basically you can think of them as like they are classes. They are just templates for objects. They even have constructors. So the main method is in the special main module, which gets the capabilities it needs from the runtime. And then it can pass them to other modules like caplog. And ultimately, if you want to do anything of importance, you need to call methods on capabilities. So here is how this program starts. First, there are only some basic capabilities which we call devices, right? You need to use those to access the real world. And to actually start the program, the runtime needs to initialize the main module and then calls its main method. And so then code can instantiate modules like caplog. And the thing is that caplog wants to access system features, but it can only ask for capabilities, right? Politely. And it has to get them from the outside, right? So that is our compartmentalization mechanism right there. We can choose what caplog gets. And in the snippet we saw, main gave caplog direct access to device capabilities, which maybe wasn't so good. And if we want to restrict what caplog can do, we need to be a bit more subtle about it. Okay, so let's say that we are reasonable and we want caplog to only access log files and nothing else. So here is a schematic example of how to do that. First, instead of giving caplog direct access to the FS device, we use the restricted FS class to only let it access a single directory. And next, instead of giving it net or eval, we give it inert versions of these capabilities, which throw on every single method call. And the way restricted FS works is very simple. On every method call, we just check if it should be allowed. If not, we throw. If yes, we forward it, right? Okay, so that's it. That's all we need. We just need to encapsulate some objects, right? So this is just standard object-oriented thinking, something that many, I wanted to say all software developers are very familiar with. And you know, the genius of object capabilities is that we are reusing this thinking to express security policies, which is exactly what makes them a very desirable approach for compartmentalization. But as I said, they do require a stop-the-world migration. So to secure an existing program with object capabilities, we need to migrate all the code in the program, including all the dependencies. And in extremum, this is very burdensome, right? So ideally, we prefer to migrate any part of the program independently of the others. So let's see how our approach promises to help with that. So fundamentally, we answer two questions. One is, how can classical code interact with code written with the object capability model? And two, what sort of access policies can we enforce when this interaction is going on? So what we want is that we want a coherent integration between packages of classical code and the object capability model, right? Now, such code can access system features, so we must act like it was a capability. There is no other way. So if a module wants a package like log4j, it needs to request it as a constructor argument, like we see. So, and for now, just ignores the hash. It means danger, and we will come back to that. So you should basically think of this as a funky import clause. Log4j doesn't have to be an object at runtime. We just treat it like it was. Next thing is that classical code accesses system features via system calls, but in object capabilities, that can only be done with devices. So to reconcile these two, we can just say that system calls are method calls to devices. So that's the picture that we should have in our heads. We act as though the log4j package was an object, and main had a reference to it, and log4j was doing its job by accessing devices, right? And we are interpreting existing code in this way, right? There is no modification to the package. Okay, so far so good, but we still need to think about one last detail, which is how do we make sure that log4j doesn't access malware from the internet? And well, we just need to put something over there. So before we could put our own objects there, but that doesn't work anymore. Okay, so the idea is that we propose enclosed blocks during which only approved system calls can be performed, right? And using those, we can make sure log4j can only access the file system, right? We just always run log4j inside of an appropriate enclosed block, right? We say, within this block, only the FS device should be accessible. So that gets translated to a list of file system-related syscalls, and if log4j tries to access the network at runtime, it gets stopped with a runtime error, right? It's like a throw on a method call. So basically, the enclosed block allows dynamically creating compartments and running untrusted code in them. And we propose these blocks because they can be efficiently implemented with enclosures, which is a technique from, recent technique from 3 years ago. Okay, so there is a bit of a caveat here, which is that this thinking has to be extended to mutable objects because they can be used to indirectly access system features, but time is short, so details are in the paper. The core idea is that we treat all mutable objects as capabilities, and we only allocate them within certain memory regions. And in concert, these allow forbidding access to SOML or mutable state with enclosed blocks, and they integrate this with the object capability model. And we also have good grounds for saying that this can be applied to controlling access to secrets kept as immutable data. Okay, so here is the recap. We saw the enclosed blocks that we saw allow dynamically creating compartments for running any classical code that we might have. And the trade-off is that they work at a very coarse granularity. And because of the way we integrated classical code with the object capability model, enclosed blocks allow reusing existing OS-level concepts, like approaches, really, like enclosures, and they still permit expressing POLA policies with language-level concepts like devices. Okay. So that brings us to the last part of the talk, which ties these two systems together. So in gradual compartmentalization, we propose to track capabilities in types, and Gradient concretely uses capture tracking for this purpose, which is another recent system, and it's the capability equivalent of an effect system. So let's just focus on how can we use that to enforce some security policies. So in this slide, we have a capture-checked version of log4j. The hash is no longer there, so this is a less dangerous variant, and that's because we can statically restrict access to devices with ascriptions. Okay, so this particular main can only access the file system device, but not the network, nor any other device, right? And that's because of the capture annotation that it has, the one after a hat. right? That's like a return type ascription, but for what capabilities can be mentioned by the body of the method, and not the value returned from the method. Okay, so if we wrote this code, we would get a compiler error because log4j accesses too much. Okay, so let's assume that we continue with some nice4j package, which makes the compiler happy because it only accesses the file system. So what we also propose are restricted blocks, which use types to statically check that only certain capabilities are accessed. This is basically the same sort of ascription. It's only on a block and not on a method. The code in this particular restricted block can only access log, and that's a way to express that this code can at most do logging, and it cannot access any other system feature, right? And it piggybacks on object capabilities. So to wrap this up, we can use these capture ascriptions to create static compartments for capture-checked code, and these work both for classical code and for object capability-based code. Okay, so let's briefly go back to log4j with the danger hash. So what that meant is that this package is not capture checked. So we want to run such code under an enclosed block, and what happens if we forget one? Well, we get a compiler error. And that works because here, now the type system tracks that all definitions in log4j are capture unchecked, right? So that's our equivalent of being dynamically typed. And we forbid main concretely from accessing capture unchecked code, either directly or indirectly, right? So this is a violation of that. Okay, and to wrap this up, if we added an enclosed block, we basically assert what devices may be accessed during this block, right? So that's our equivalent of a dynamic type check, but on access to capabilities. Okay, so the last recap is that tracking capabilities in types allows statically enforcing the POLA on packages of classical code, and that code does need to be capture checked, but that's much easier than a full migration to object capabilities. Okay, so we saw that what gradual compartmentalization and gradient are about. Let's finally talk about our other results. So we develop the formal foundations for the approach. That's the other major contribution. We take the core capture calculus and we extend it with quite a number of features necessary to support gradient. So we add mutability, we add modules, we add object foundations, and on top of that, we also propose this gradual capture tracking idea. And we prove that the resulting system is sound. Okay, so also a few words about how we validated our approach. I promised that capture checking a package is not too much work. That's why we chose capture tracking, because it was designed to require less annotations than an effect system. And to validate that, we migrated an existing Scala library. And the result of that is that no major refactoring was necessary, and most of the lines that needed updating were very trivial, and in general, few lines had to be changed. Other than that, we also provide a detailed description of how gradient can be implemented based on existing literature, and we evaluate the performance of an enclosure-based implementation. Okay, good. Thank you for your attention.
Do we have questions for Alex? James?
Thank you for a great talk and some obviously really interesting work. I've actually got two questions. The first one is when you talk, and I'm still somewhat confused, I'm jet lagged more than usual today. You said things were like dynamic checks. Did you mean that they were dynamic checks? So when you're encapsulating the classical code, because you're talking about a performance overhead there.
Yeah, I mean, so right here, we would have a dynamic check, right? So that's basically what I was saying.
Does not have a dynamic check.
Okay, sorry. No, I won't scroll back over there. But basically, over here, this body of main can only perform file system related syscalls, right? So that's a dynamic check.
Right, so effectively what you're doing is injecting the object capability for the file system into what Mark Miller would call the sort of ambient authority. So now
it's like a reverse dependency, right? But yeah, you could view it as like saying that within this block we have at most this amount of ambient authority.
well, within this block we can get access to FS even if we haven't been passed it.
Basically, yes, but only FS.
Right, right. I shouldn't say implicit. The other question I was going to ask is, how do you think this relates to the sort of effect handler stuff that's going into OCaml and the functional people seem to love? And if you just sigh, that'll probably do.
Okay, do you want a particular part of an answer to that question, or?
Well, ideally, I'd want one sentence that says something like, I don't know, object capabilities are effect handlers done without control flow inversion, but I don't know.
Yeah, I mean, yeah, that's what you could do. So, like, I think that something like this form of gradual typing should also be possible there, right? And like similar sort of enforcement should be possible. And so basically, you can view handlers like they are like objects passed around, right? It's
right.
Sorry, I'm
right,
maybe
which
moving
is
a bit too fast.
Right. Okay. I mean, we should probably take it offline, but you know.
Yeah, it would be great to chat about that.
All right, let's thank Alex again. Right, and our fourth speaker in this session is Chung-Ha, who is going to talk to us about automatically reducing privilege for access control policies.
Okay. Yeah, hi, I'm Chung-Ha, and in this talk, I'm going to present the how we automatically refine permissions of IAM policy in AWS. So in AWS, customers deal with access controls with various types of resources and services. Especially this access control is about who has access to what resources. So to support this access control, AWS customers use AWS IAM policy. AWS Cloud's access controls is determined by IAM policy, and this policy language provides the fine-grained access controls. So when writing these IAM policies, it is important to give least privilege. And least privilege means you need to grant only required permissions to perform a task. So in AWS, there are security best practices emphasizing that least privilege is important and some ways to achieve it. Usually what AWS user does is they write the broad permissions when writing IAM policies, since they don't have exact information of required permissions at the beginning. And then they achieve the least privilege by removing unnecessary permissions by updating the IAM policies they wrote. But manual policy update is not trivial because it requires the understanding of necessary or unnecessary permissions. So to help this direction, we present this IAM policy refiner. IAM policy refiner helps to modify policies to remove permissions automatically. And it takes the user IAM policy to refine. And it takes another input, which is access data for a certain period of time. And this access data is useful for refinement because it gives an indication of what permissions are actually required. And our technique has been applied to a production setting of AWS IAM Access Analyzer to recommend IAM policies based on unused permissions. And for this service, IAM policy is applied with a very specific setting, but in this talk, I'm going to talk about the general approach of IAM policy refiner. So I mentioned IAM policy refiner takes the IAM policy input as an input with access data and refine it. But we haven't answered this question. What is the right way of refining policy? So let me use a visualization to better understand it. Here, the orange circle shows all possible requests allowed by the input policy, and this green area shows the actual access data. And our goal is to find out the right level of refined policy. Basically, our journey is about finding the simplest refinement from the input policy and achieving the right level of refinement. So for that, we defined 3 properties that should be satisfied by a refined policy. They are readability, soundness, and tightness. So in this talk, I'll use very simple example without any formal notations to describe these, but we actually formally define this in our paper, so please check out our paper if you're interested. And in our setting, basically, this white level refinement is the least permissive policy that is readable and sound. So let's explore these properties with an IAM policy example. And here is a simplified structure of IAM policy, and I kept only details required to understand our technique. So policy consists of multiple statements, and each statement defines various elements such as effect, action, resource, IP address, or other types of elements. And each element uses the patterns to match values from requests. So let's take a look what this statement does. First, effect defines whether the statement is about allowing requests or denying requests. It says allow. So it is about this statement is about allowing requests. And this action element has these 2 string patterns, encrypt and decrypt, meaning the action value for the request should be either encrypt or decrypt to be allowed. And this resource element uses my_key-star. And the star here means in IAM policy is a wildcard for any length of any character. So that means the resource value from request should start with my_key-. And here last one is the IP address that specifies the specific range of the IP address, meaning the request should come from this range. So this means all elements of request values should be matched with these patterns in this statement in a conjunctive way to be allowed. Since we understand the basic concept of IAM policy, let's think about a possible simple refinement based on access data. And this left side shows the input policy I showed. And now we have this access data. This access data consists of 2 requests. And one thing we can think of in terms of refinement is we can refine the policy to match exactly on the access data. So this refined policy has 2 statements, and each statement is the one-on-one exact match for the request. First request to the first statement and second to second. For example, the first statement exactly matches the value of the resource from the first request by having my_key-111 instead of my_key-star. And similar thing happens to the second statement by having my_key-222. And also, it added one more element named account ID, and that is coming from access data. So it looks like this refined policy allows the exact request from access data, and it is kind of refined version from the input policy. But this kind of approach, when we use this kind of approach, what is the problem? The refined policy is structurally different from the input policy, making it unreadable. If we give this policy to authors of the input policy, they are not able to understand what's changed from the input policy. And another problem of this kind of structure change is it might lead to overfitting policy to access data. So this policy might miss future access requests if the access data is not complete. So for that, we define the property named the readability. This property says the refined policy should not add a new statement, and no element should be added to these statements. For example, account ID from the previous example shouldn't be added. So with the same input policy and the access data, now we have this refined policy structure. This refined policy would keep the statement without adding new statements. And it will have the same set of elements. In this example, we have this ... on the patterns of refined policy since we haven't discussed how to achieve these patterns yet. So basically, this readability keeps the syntactical structure of the input policy by avoiding the overfitting issues. And this property limits the policy refinement in a specific way since we only need to refine the existing element patterns. So let's talk about how to achieve this readable refined policy. Intuition of getting readable refined policies, we interpret each element pattern as a predicate. And because of the IAM policy semantics, if we have more restrict predicate for each element, the statement will match less number of requests. And this results in matching less number of requests for policy. So basically, we reduce the problem of refining policies into refining statements. And these refining statements can be reduced to the problem of refining predicates. So our goal is to find sound and tight predicates. And this would result in achieving the right level of refined policy. And let's look at what these sound and tight predicates are. Sound predicate means the predicate should be less permissive than original predicate, and it should allow all the requests. This is the same policy and access data I have showed. And since the requests are already allowed by the input policy here, we refine predicate with the exact matched request values. So we have this my-key-star in the input policy, and we have values from request my-key-111 and my-key-222 from resource element. So basically, we use these values to refine my-key-star to this by having this refined policy. And this predicate should allow all matched values, which are my-key-111 and 222. So in this way, we achieve the sound predicate. To better understand, let's assume we have more statements and more longer requests. In a similar way, we can map the statements to the matched requests so that we can refine each predicate with the matched values from the matched request. So let's talk about tight predicate. The tightness defines the least permissive predicate among sound predicates. And this is very useful property when finding the least permissive policy, since that's our goal in the refinement. And from the same example, you can think of many possible predicates for this resource element that are sound. For example, we can choose my-key-, question mark, question mark, question mark. And question mark in IAM policy is a wildcard for single length of any character. Another candidate can be my-key-, question mark, star. And also, we can keep the same predicate from the input policy, which is my-key-, star. So what is the least permissive predicate, and how do we find this? So we understand this problem as a lattice problem. First, we have this top and bottom, where this top is the most general predicate from the input policy, and which is my-key-, and bottom is nothing's matched. Then we have these two request values, my-key-111 and my-key-222. We can interpret these values as a predicate too. And we can keep constructing these lattice with the possible predicates, such as my-key-, question mark, question mark, question mark, or my-key-, question mark, question mark, star. So when the value is closer to the bottom, it is more restrict pattern. And we can use partial order to find the least permissive predicate. So this is intuitive. Basically, we find the my-key-, question mark, question mark, question mark is the lowest point in this lattice, and that is above both my-key-111 and my-key-222, meaning it allows both of these. So basically, this is the join operation of lattice of two values. So our solution is we can define appropriate lattice with join operation for all possible element predicates in this IAM policy. For example, we provide the join operation for equal, not equal, numeric comparison, regex with wildcards, and IP masks. Then we can find the least permissive predicates, and that helps to us find least permissive and sound policy. And to achieve this lattice-based approach, we designed this join operation to be associative and commutative. It means the order doesn't matter applying these join operations. So we can actually parallelize this approach when there are a lot of requests. So here's the recap of IAM policy refiner's technique. So we define these three properties: readability, soundness, and tightness. And we define the right level of refined policy. And we reduce the problem of this refining policy into smaller problem, which is refining predicates. Let's switch our gear to the evaluation section. We evaluated this IAM policy refiner with 3 months of access data from AWS CloudShell logs for AWS IAM roles. And each IAM role can have multiple policies attached, so we refine these policies with this access data. We chose these 3 months of data because it gives enough behavioral applications, and we can understand the indication of required permissions. And we conducted various research questions in our paper, but let's focus on these 3 in this talk. First, IAM policy should reduce the permissions effectively, and it should be parallelizable. Also, the refined policy should avoid overfitting. And here's the experimental table. The first column shows the name of the IAM roles, and the second column shows the number of requests to refine the policies attached to each role. Let's look at the number of actions columns. They show the number of actions allowed before and after refinement. On average, around 77% of actions are actually removed. For example, there was a drastic case, reduction from 726 actions allowed, now is 20 actions. And number of resource columns show how many resources values are actually refined. On average, we found 88% of resource values are actually removed or refined. And the time columns shows the execution time between running this with 1 CPU versus 96 virtual CPUs. And we saw 8.7 times improvement on this parallelization. And this particular case shows it took around 75 seconds to complete the job. Now it takes around 5 seconds with parallelization. And to check the overfitting, we split the 3 months of access data into training set and test set. We use the training set to refine the policies, and we use the remained access data to test how much of them are actually allowed by this refined policy. And here it shows we used first 10% of the access data for refining policies, and 90% of data were to check if the refined policy can allow them. And by increasing the test data, we check when the refined policy can allow all the remaining access data, such as 20% of refined policy and 80% for checking refined policy. So based on our results, we saw 50% of requests were enough to avoid overfitting, and refined policy, which is around 2 months of data. Here's the conclusion. We presented IAM policy finder that automatically refines IAM policies with access data, and we define this right level of refinement with the readability, soundness, and property, these 3 properties. And by reducing the problem of refining policies into refining predicates, we could tackle this smaller problem with these predicates. And we checked the effectiveness of approach on real-world AWS access data. As a highlight, specific setting of IAM policy finder has been applied to a production setting. And our paper explains these settings. So please check out our paper. Thanks for listening to this, and please reach out to me or our team members if you have any questions on this service or work. Thanks.
Questions?
Right. So I was wondering if, because the lattice that you show it was carefully designed. Like the more you go up, the less information you have, right? But does it happen in practice? Like when you need to enumerate the resources example, you're now with a very long list of. If you go back to the slide where you say resource.
Here?
Yeah. So. Can it happen that in the resource you just put like one element in resource? It's like with the question mark, or star, or a specific thing. Can it happen that there are cases where you need to put a list of resources, or that doesn't happen in your approach?
Oh, right. So IAM policy syntax allows this list of resources with each of them can be regex, and same thing can be applied. We can actually map the match request to the corresponding target resource patterns, the predicate, and then we refine each of them.
Because I'm thinking like, you want readability, right? So if you have a list of resources, you don't want a list of 2,000 resources. You want to perhaps generalize the resources so that the list gets smaller in terms of readability.
Right, but in terms of like refinement here, we don't change the number of research patterns that exist in the input policy, and we keep the number of
Okay, you keep the you keep the
yeah,
number.
but I mean, you have a good point on the having this enumerating this or refining those. I mean, those can be defined by the readability property.
Because that will give you, because here you always go up in the lattice, but if you have this kind of constraints, you might go up and down, depends on readability. That's
Yeah,
kind of
right.
my
I
insight.
mean, the customization can be applied here by how we design this lattice-based approach.
Okay, cool,
Yeah.
thanks.
Thanks for the good question.
Thanks for the talk. Does the policy refiner support refining principles? For example, if you have an EKS node group in the policy, but only one node is ever used to use that policy.
Okay, that is a very good question with the knowledge of AWS. Yeah, current approach doesn't support the principle. And that's kind of future work because the principle doesn't work in the same way as a resource or actions by having these regex because the format patterns of the principles can change based on the roles or users or groups. So yeah, so that's kind of approach we are looking at right now.
Cool,
Yeah.
thank you.
All right, let's thank Chunga again. So our fifth and final speaker in this session is going to be Danielle, who is going to be talking to us about functional ownership with fractional permissions. No, sorry, I botched that. I'll have to look at my cheat sheet. Functional ownership through fractional uniqueness. Sorry.
Sure. Oh wow, that's a lot louder. What borrowing allows us to do is it lets us split these capabilities up into pieces. So what we can say is, for example, if I take an immutable borrower, then I'm passing on part of the capability to the borrower. I'm allowed to read from the value. The borrower is allowed to read from the value, but neither of us is allowed to write because that could lead to data races and other kinds of memory safety problems. On the other hand, if we take a mutable borrower, what that means is the borrower gets the whole capability, so they can read from the value, write to the value, whatever they want. But I'm no longer allowed to access the value at all because then I could read while the borrower is writing, for example. I can't do any of that until I get the full capability back. So let's just have a quick look at how that looks in some simple Rust examples to make sure we've got the idea. We're going to just use a simple struct representing a color. So we have RGB values, and we have one example of a color which happens to be the nice shade of granule blue. I'm not advertising in this talk or anything. So here we take two immutable borrowers, and this is totally fine because X and Y are both only allowed to read from the value. They're not allowed to write or do anything dangerous. On the other hand, we wouldn't be allowed to take two mutable borrowers because this, again, could lead to data races or similar problems. And similarly, we're not even allowed to take one mutable borrower and one immutable borrower because in this example, X could read whilst Y is writing, and that could lead to problems. One interesting thing we are allowed to do, though, and this is something that we are going to represent in our system, is we can take one mutable borrower, and then we can take a mutable borrower of that mutable borrower, and this is all fine because the full capability gets passed along the chain at each step. So in the end of, in this example, Y ends up with the capability to read and write, but X and Granule both have no access until the capability gets passed back along the chain. So how are we going to represent these ideas in Granule, which it has a very different basis? Well, first let's have a look at what already exists in Granule and go from there. And we're going to start with linear types. So the analogy I always like to use when I explain linear types is that a linear thing is like a delicious piece of cake. Why is that? Well, we live in a sad world where if we have some cake, we can only eat it once and then it's gone. But if someone bakes us a cake, we're probably going to have to eat it, otherwise they might be disappointed. And here's how that idea looks in our language, Granule. So on the left-hand side, we take in an input value of type cake. On the right-hand side, we eat our cake, which makes us happy, and we have our cake, which means that we have a cake. So this, we just interpreted this as a sort of standard Haskell program, which it looks a bit like, this would be allowed. But in Granule, everything is linear by default, so this is not allowed because we use the cake value twice on the right-hand side of the function, and we're not allowed to have our cake and eat it too. But this is not all Granule can do, because sometimes we want to go beyond linearity. Not everything is used in a linear way. Even in linear logic, this is true, because we have the bang modality, which tells us we have something that can be used any number of times in a nonlinear way. But this binary view can be kind of restrictive. We don't know anything about how a nonlinear thing is going to be used. So we could generalize from there to bounded linear logic, which came about not too long after linear logic. And this gives us a whole family of modalities, which are indexed by this thing R, and R just gives us an upper bound on how many times something is going to be used. So for example, I could have something that will be used at most twice or at most 3 times and so on. What graded model types let us do, and these are sort of the type system that really underlies Granule, is they go even further. So now we grade or index the modality by something from a general algebraic structure called a preordered semiring, and depending on which semiring we choose, we get different properties that hold true about our types. And I'm going to show you some examples of this, but just a quick notational point first. In Granule code, rather than having a prefix modality where the grade comes after the box, in Granule code we have a postfix modality where the grade comes inside the box. So that's how you're going to see it appear on the next slide. The first example we're going to look at is a simple semiring that only has 3 elements, 0, 1, and many, sometimes called non, 1, and tons, thanks to Conor McBride. So 0 means used 0 times, 1 surprisingly means used 1 time, many means used any number of times, just like bang. So here in this example, this says that we have lots of cake, we eat one of those cakes, and we still have lots of cake, much happier than the example we had before. We also have an exact usage semiring, so this is the semiring of natural numbers. So if you think back to when you were a small child, you probably remember being told at least once that if you have 2 cakes and you eat one of those cakes, then you'll have 1 cake left. Or if you prefer, you can think back to when you were a slightly older child, when you were probably told that if you have n plus 1 cakes and you eat one of those cakes, then you have n cakes remaining. So by using polymorphism on the grade here, we can be slightly more general about what we're saying. Just one more example to show you kind of the power of grades, a little bit more interesting. In this example, the first input value is maybe a cake or maybe not. The second input value is a cake with this new interval grade, which goes from 0 to 1. And on the first line of the function, if we don't have the first cake, then we eat the second cake. On the second line, if we do have the first cake, then we eat that cake and don't worry about the second cake. And both of these lines are allowed because what the interval grade means is we can use that value any number of times between 0 and 1. And so since both of those lines follow that rule, this function is accepted. So that's a few examples of grades, but it's not clear how we're going to link this to the ownership ideas that we mentioned earlier on. And in order to do that, we're going to have to start by thinking about what the relationship is between linearity and uniqueness, which are 2 ideas that are sort of well understood to be related, but the exact relationship was something that we thought more about in our ESOP paper a couple of years ago, which was called Linearity and Uniqueness, an Entente Cordiale. So if you look around in the literature, you find a lot of different views on what exactly the relationship is here. Some places will tell you that these things are just variants of each other. Some places will tell you that these things are dual to one another. And these are both kind of right in some ways and not entirely clear in others. The takeaway that we came to, that we found useful for explaining this, is that uniqueness is a guarantee about what's happened to a value in the past. That's how we know that we have the only reference to a value, because it's never been duplicated before, and so it's safe to do what we need to do. Whereas linearity doesn't tell us anything about what's happened in the past. Something could have come from inside a bang modality, and therefore there could be any number of references. But what it does tell us is that that value is never going to be thrown away or duplicated in the future. And so that's where we get this kind of dual relationship from. But also, this gives us the key takeaway we need to put both of these kinds of value into a single system, as in Granule. We have linear values as the base, as we've already seen. We have the bang modality, which gives us Cartesian or unrestricted values, just like in standard linear logic or linear types. And we also have this third kind of unique values, which we represent with this additional star modality. We can always go from unrestricted to linear, just as in linear logic. We can go from unique to nonlinear by forgetting the uniqueness guarantee. but we can't always go back in the other direction. The only way we can ever go back is if we make a deep copy of a value, and then we know that the copy we have the only reference to the copy. So it's safe in that case, but not safe in the general case. So this is great. We understand linearity and uniqueness, and this is where we got to 2 years ago. But now we want to think about how can we extend this to represent these more complicated ideas by introducing borrowing. And the way we're going to do this is exactly as I explained on the previous slides. We're going to introduce a grade onto this modality, and we're going to use the grade to represent how much of the capability a reference has access to at the moment. And the way that we're going to do this is based on ideas from Boylan's fractional permissions. So first of all, let's look at mutable borrowers. This is our with borrower function, which says that if we have something that's unique and we have a continuation which tells us how to use a borrowed version of that thing, then we can pass in the unique thing and get a unique thing of the new type back. All the computation happens inside a continuation here to sort of enforce the lifetime of the borrower and make sure the borrowed thing doesn't escape from what's happening inside there. Once we've done this mutable borrower, we can then go from there to immutable borrowers by interacting with this grade. So you can see in the with borrow example, we have a grade of 1. The 1 grade means we're allowed to do whatever we want because we have the whole capability. But now we introduce these two functions, split and join, which let us interact with that grade. So we can increase the number of references or decrease the number of references. If we add a new reference, then we split that capability in half. So now each reference has part of the capability. We're only allowed to read, we're not allowed to write. And then we can join those capabilities back together whenever we like, and it's only when we go back to the full capability of 1 that we're allowed to mutate the value again. Notice that this also gives us this kind of reborrowing behavior, because I can split that fraction as many times as I like and get a quarter, an eighth, and so on. All of those have the same property that we're only allowed to read, and it's only when we get back to 1 that we can write again. Now, does this work in the granular implementation? Yes, it does. We have an artifact for this paper that you can play around with. You can also download the regular build of Granule from the website. I don't think this stuff is quite in there yet, but it will be very soon. So watch out for that. But just to give you a quick example, here we define a data type for a color, just like we had with the previous Rust examples earlier on. And let's hypothesize that we have some function that makes use of a borrowed reference to a color. Let's say that it doesn't do any mutation, so we can do this with NA kind of fraction f. Then here's an example that uses all of those primitives that I showed on the previous slide. So we take a unique reference, Granule, we borrow that, so we get a mutable borrower b. We split that into two immutable borrowers, x and y. We apply this observe function to one of those, and then we join them back together to get back to the unique ownership. Just a toy example, but just illustrating that all of these primitives kind of interact with each other in this way. And everything checks out and type checks. So, other stuff that's in the paper, there's a lot that I didn't get to talk about. First of all, the toy example is great, but obviously we want some kind of more practical stuff. And to do that, we have a couple of different interfaces for resources that we can play around with. So we have polymorphic references, which can point to values of any type. We also have mutable arrays of floating point numbers, which you can read from, write to various indexes, and so on. And the way that these are implemented, we also have identifiers for these that have existential types, and what these are for is to make sure you don't join together references to two different arrays, for example. So there's a lot of interesting stuff that goes on there. You'll have to read the paper to find out more. We also have what's called partial borrowing. So imagine if you had, for example, the color struct on the previous slide and you wanted to just borrow the red component or the green component and leave the rest with the original owner. Well, we have these push and pull primitives that allow you to do this by distributing the modality inside and outside of products. So again, something that you can look at the paper to find out more about. Last thing I should probably mention is this isn't just an implementation thing. Obviously, we formalized all of this, so there's some meta theory behind it. We have an operational model, which is based on the idea of heaps. So we have a heap that tracks the grade that's associated with each value, but now also the permission that's associated with each reference. So this is where all the fractions get stored as well as the grades. We use a call by value semantics, which is kind of different from some previous work on graded types that used call by need. So there are some interesting new challenges that come about when you try and do these things in call by value. Details on that, you'll have to read into the paper to find out more, because there's a lot of fun stuff that goes on there. But some of the key properties we prove using this semantics. We have the standard progress and preservation properties. Not too much interesting going on there. We also have borrow safety, which basically, in sort of simple terms, says that the permission or the capability, the total amount of capability gets preserved in each reduction step. So when you start with the full capability, that can get split or joined an arbitrary number of times, but we're always going to get back to the full capability at the end. And we have this kind of uniqueness property, which we talked about in our ESOP paper, but this property now just follows as a sort of direct corollary of the borrower safety property. So this says that if I start with a unique reference to something, eventually I'm going to get that unique reference back as the original owner. And that's what lets us do all this fun stuff while still preserving the nice memory safety properties that we want to have. So that's most of what I wanted to say, just a quick summary of the big ideas. First of all, linearity is a restriction on the future, while uniqueness is a guarantee about what's happened to something in the past. So similar in some ways, different in some ways. This is the kind of the key takeaway about what's going on there. Quantitative types are a generalization of linear types which let us be precise about how exactly a variable is going to be used, maybe exactly how many times, maybe some other property. Meanwhile, borrowing is a generalization of uniqueness types, so kind of conversely to the linear case. It lets us be more flexible, so it lets us create more than one reference while still making sure that if we do get all the references back, we'll know we've got them all back, and so we can regain that kind of ability to do what we like while still preserving memory safety. And finally, graded types, as in Granule, are a really flexible, powerful framework. They can encompass all of these ideas that I've talked about, also a bunch more stuff that you can look at in our other work. Here's where you can find out more about what's going on in Granule. I do recommend you have a look. Here's where you can find out more about me, get in touch with me, and so on. Otherwise, thank you for listening.
Thank you for the very interesting talk. I really like how you rigorously describe what borrowing is. I have maybe a question about this detail. So does it make sense in your system to talk about something that's simultaneously linear and unique? Because based on this description, it sounds like it makes sense to have both.
Yes. So it's not something we really provide for as like a natural thing in our system. You can have things that happen to be both unique and linear, and that's fine, but we don't sort of represent that as a modality in and of itself, which is basically just a detail of how we chose to implement it. You could imagine doing it in a different way that did focus on that, and I guess it depends on your use case whether that would be more useful or whether it's more useful to keep things mostly separate as we have done.
Right, thank you.
Yeah, thanks for that. Lovely work and a lovely talk. And I'm really trying to get cakeism into my question, but I can't work out how. For those who don't know, one of your many previous prime ministers in the last 6 minutes said he was in favor of having his cake and eating it, which of course is the complaint that functional people have about object-oriented programmers. The question I had is, I noticed when you were talking about mutable borrows,
Yes.
you said that the mutable borrow gets all the capability. So, and again, I'm not quite sure I have the right language for this. How does that differ from what would be a move semantics? Because if you're modeling an object move in something like fractional permissions, that would be the same thing.
Yes, so this is a good question because it's not strictly true to say that it gets the full capability. That's kind of I guess a slip or a mistake on my part. A mutable borrow is kind of different from having the unique ownership because while you can read from the value and write to the value, you don't have the ability to like throw that value away, get rid of it permanently because the unique owner needs to get that value back. So there is a distinction between actually owning the value and being able to really do what you want with it and having the capability to read to and write from it, which is when you have the sort of one permission here. But that doesn't give you all of the permissions to like throw it away and do that kind of thing. So there is more of a distinction there.
That's a great answer. It almost comes back to go back and read the other John Boylan paper from 2000 and something. It's had some other weird guy from New Zealand as the other author.
Yeah.
Hi, Will from Brown. So this is really cool, and I want to better understand the design goals. So is it more that there are, say, programs inexpressible in Rust that you are trying to show you can type check in Granule, or is it more that just what would a Rust-like type system look like if you pulled it more into an ML-style language? Like which direction better characterizes the goals of Granule?
Much more the second of the two things that you said. We're definitely not trying to express programs, ownership-based programs that you can't express in Rust. Rust can obviously express a bunch of things that this can't express, not least non-lexical lifetimes and things like that, which we don't have any way to model in this system. Mostly what we're trying to do is sort of get a better understanding of how ownership and borrowing relates to these kind of linearity and graded types ideas, and to do that by sort of having a system that can express both of those two things. And so that's kind of what we're aiming for here. Obviously, this only sort of covers the basic ownership and borrowing ideas of just standard mutable borrowers, immutable borrowers, reborrowing, and so on. There's plenty more you could do. Maybe we will go back and do some of that stuff. Maybe someone else will do some of that stuff. But yeah, that's the direction that we're coming from, rather than trying to outcompete Rust in its own domain. I think that would be a silly idea for Granule to try and do.
Okay, thanks.
Hi. First of all, I really like the Ferris emojis. They're very cute. Maybe you went a little bit too fast for me, but could I ask you to just briefly summarize, I guess, how graded types distinguishes itself from something like reference counting?
Yes. Well, first of all, sorry if I went too fast, but if I had more than 15 minutes, I would have gone slightly slower. But yeah, so how does graded types distinguish itself from reference counting? Well, reference counting is often a dynamic kind of thing, right? So at runtime, you're kind of counting the number of references that exist and doing things based on that. Whereas here, we're doing everything statically. So here we've got the sort of fractions directly in the types, and so everything's being sort of checked before the program ever gets run. So I guess the argument about which one of those is better is kind of the same argument about whether we want to do static type checking or whether we want to do dynamic runtime checks. Probably depends on your use case as to which one of those makes more sense, depends what you're doing, but yeah.
Awesome, thank you.
Yeah, great talk. Quick question. In the join type, I couldn't see that both borrow come from the same value of the type A.
Yes.
How do you ensure that? Because in the type signature, I couldn't see that.
Yes, so that's mostly managed rather than through the type signature of join, but instead through the type signatures in the actual interfaces for the resources. So for example, when you create a reference to an array or a reference to some other value and so on, those references come along with identifiers, and as I only mentioned very briefly, but those identifiers tell you which kind of value you're working with. So that's where the existential types come in those interfaces.
Right, thanks.
No problem.
All right, let's thank Daniel again. So this concludes this session. Thanks for coming, and please go and enjoy lunch.
Testing? Okay. Hi, everyone. So we're going to get started. This is the 140 session as Performance Analysis and Optimization 1. So we have a really exciting set of talks in this session. And we're going to start out with a talk by Suman Jana. And the work is on accurate data race prediction in the Linux kernel through sparse Fourier learning. Yeah. Now? It's working? Okay. Let's get started. Thank you, Suman.
All right. Thank you. Thanks, Manu, for the introduction. Can everybody hear me in the back? All good? All right. Okay. So I'm Suman Jana, and I'm presenting this work. This is jointly done with all my students, Gabe Ryan, Burju Jatin, and Gabe graduated and has since joined Microsoft Research, but due to some family emergency, I'm the one presenting the paper. So thank you. Thanks for attending. All right. So let's first define the background of the problem. And this is a fairly well-known problem. I'm sure all of us know what data races are. But just to recap, data races happen when two memory accesses are performed to the same address by two different threads, right? And at least one of them is a write. And we are more specifically interested in data races in the context of Linux kernel. And obviously, here is an example of the kind of data races we are talking about. So in this particular case, as you can see, there's a variable that's being accessed. It's protected by a mutex, right? So as you can imagine, most of the simple classic data race bugs have been thankfully filtered out from the kernel. It's a widely used piece of software. But there are more subtle bugs, right? So here, the bug is that the mutex that's protecting this is actually a variable that's passed from the function, right? So two callers might pass two different mutexes, sorry, and it will still race, right? So this is exactly what happens in this context. So you have this net struct. So you have the mutex, but these are two different mutexes, okay? Right, so this is an example of the kind of relatively subtle bugs that often happen in the Linux kernel. Okay, so these are the kind of things we are focusing on. And why Linux kernel? That's the question. So in terms of our techniques, it's generic, but we focus specifically on Linux kernel, partly because one is it's a very popular software, large attack surface. It has been engineered to be reentrant over the years for performance reasons, right? And also my home community is in security, so I care a lot more about security, right? So Linux kernel, often these bugs have pretty severe security implications. So that's why we often work in this area. And of course, there are many users, as we all know, all right? So that's that. All right, so of course, race detection is a very old area. There's a lot of work. I won't have time to summarize all of it, but I'm gonna talk about two samples to give the flavor of kind of work that is going on to detect this sort of kernel data races, right? So what's the main problem here? The main problem here that we are doing multi-trace race prediction. Because remember, in the Linux kernel, there are different system calls that are happening, right? So the user programs are making system calls, and these are reentrant, right? That means they run in concurrent threads. So what we are interested in are two different things. One is different sets of inputs. Remember, inputs in this context is inputs to the kernel. All the system call arguments, the system calls, they are inputs, right, in this context. And then the schedules, right? Obviously, the schedules are across these threads, right, which are running inside kernel for individual user programs making system calls, right? So essentially, one has to try all different combination of different inputs and different schedules. And it blows up, obviously, as you can imagine. This blows up exponentially, right? So this is the challenge. And so the practical work in this field, the main goal is, given a fixed computational budget, you want to maximize the number of detected races, right? So that's kind of the goal. And there are several approaches, but again, as I said, I'm gonna give two quick examples of the kind of thing I'm talking about. The first is what is called concurrency fuzzing. The key idea is that you have a kernel fuzzer that generates code coverage guided trace corpus. That means, maximizing code coverage as you're generating this trace corpus. And then for each of these traces that have been collected as part of the corpus, there will be another fuzzing component that will try different schedule, try to create races and detect races. Right? So this is the approach. Problem is that the search space is too big, and often the guidance of concurrency coverage, often they will try to maximize things like alias coverage, right? It doesn't quite get the bugs, right? So the problem is it has a very high number of false negatives. It misses a bunch of stuff. The other alternative approach, again, operates on the trace corpus, but on the trace corpus, instead of fuzzing for schedule, it does alias detection, right? So this is static. So this is good from not missing stuff, but it catches a lot of stuff that are false positive, right? So that's kind of the problem. And once it detects these aliases, it's going to try to recreate the races, right? And often that won't happen, because in reality, when you create an execution, that's not always feasible, because you are ignoring a lot of dependencies in terms of changing execution path, changing heap allocations, changing pointer values, all sorts of dependencies. All right. So this essentially will have a lot of false positives, and as you run to reproduce these races, this false positive can be cut, but there will be a lot of computational overhead. You'll basically waste a lot of time on bugs that are not real bugs. Right. So that's the problem. Again, I'm not going to spend too much time summarizing this, but I guess I already said, high precision, low coverage is the first approach's deal. The second approach is high coverage, low precision, right? And both end up wasting most executions on not finding bugs, right? All right, so what is our approach? Our approach overall is based on a learning framework. So we are going to use a learning approach to this problem. So as I said, the basic problem is that you have a target program, in this case Linux kernel obviously, but we assume that we can generate a bunch of trace corpus using some coverage guided mechanism. So that's not our contribution. That part we assume will be given to us, right? And then we want to approximate an indicator function that will take input and trace and predict whether it's feasible or not, okay? And the way we do this is this indicator function will be decomposed into two parts. One is an encoding function, because these traces are very large, and we only care about certain instructions, like memory instructions, synchronization primitive, stuff like that. So we have an encoding function, phi, and then we have a learned approximation function, which will tell us whether it's feasible or not. That's the model. F star is learned, and phi is a hand-coded function. It's essentially, you can think of it as feature set, right? It encodes the features. Right? Okay, so that's that. And then in terms of the learning framework, the overall idea will work like this. You have a trace corpus E given. You will learn based on the phi of E. Remember, phi is manually designed, right? And then we'll learn F star to predict if any candidate trace is feasible or not between 0 and 1. And then on the side, we'll have synthesize candidate racing traces, right? And schedule E star based on some sort of conservative but cheap analysis, right? We use logset for this purpose. And then we'll feed it the predicted, the candidate racing schedule and traces to this learned function that we have. And if it predicts with high confidence that it is feasible, only then we are going to try to recreate that race, right? And if it's recreated, we are going to output the race and schedule together to say this is a bug. All right. So the whole goal obviously is to have no false positive, but want to be efficient as well. Those are the trade-off we are dealing with. Right? Okay. So that's the big idea. Of course, this framework is generic, but in our context, we're going to use something called Fourier learning. We're going to talk a bit more about it later, instead of, I guess, the more popular LLMs these days, right? I mean, the obvious question at this point, obviously, I said learning, why not LLMs? Because in this particular context, we wanted to achieve, high sample and parameter efficiency. We want the model to be small. One of the benefit of Fourier learning is that it explicitly uses sparsity to keep the model small, the number of parameters, and in our context, we have evidence that the data is sparse. The dependencies are very sparse. That means each memory access only depends on few other memory accesses, and this has been observed before by other work too. And it also has some other benefits, like it can support continual learning or incremental updates quite well. And this is, remember, in our context, because the corpus will get updated, there will be more traces coming in. We will be able to fit it more easily. Okay, so that's two of the main benefits of this. So this work, the current work I'm presenting, builds on our prior work. So I'll briefly summarize this. This was published in last year, Oakland. We basically had the predictor, the learned function, predict what I call stable set. That means the system calls that will always be performed with high probability. These are good because if there is any race here, it will, it has high likelihood to show up irrespective of the different interactions that might happen. So that was good. But the problem was that it cannot identify many races. So whatever it predicts well, but it cannot predict a bunch of other stuff that are not stable, and that depends on what kind of inter-thread communication that might happen. So that's the focus of this work. This is what we are trying to get at, okay? So this is an example. You have a trace with aliased access. Now, depending on the communication, this may or may not happen, right? So in this particular case, because the flag is set to 1, it won't happen, right? But in a different schedule, it can happen, right? So this will be missed by our prior work. This is what we're trying to find, okay? Right, so, and of course, in order to do this, we need to deal with both control flow and address dependencies. Here is an example of a control flow dependency, and here is another example of a memory dependency. This kind of code is fairly common in the kernel. Right? Okay, so what we are gonna do, we are gonna approximate a feasibility function of E as ordered pairs of memory accesses. Basically, we want to predict whether these ordered pairs of memory accesses are feasible or not. And we are going to do this Boolean encoding, and we are going to try to learn their feasibility. So given an ordered pair, if it's feasible or not, okay? And the details are in the paper, when I'm not going to cover that much, all right? Okay, so we need to learn this feasibility function based on the observed set of traces, right? And each trace, remember, has a bunch of ordered accesses, all right? So we are going to encode this into the Boolean domain because as I specified, right? So we are going to get Boolean vectors. And then from these Boolean vectors, the Fourier learning will map it to R, right? A real value between 0 and 1, all right? And 1 means feasible, 0 means not feasible. Something in the middle is less feasible or more feasible. All right, so that's that. I'm not going to go into too much into the details due to the time constraints, but do check out the paper for more details. And the key observation why this works is because most of the Boolean functions that we are dealing with, essentially these ordered memory accesses, are sparse in the Fourier domain. That means most of them can be approximated by just a few Fourier coefficients. These are the parameters. So this is efficient as long as it's sparse, obviously. And we use a low degree approximation to keep it efficient. Okay, this is fairly standard stuff. It's just that this kind of sparsity empirically has been confirmed in this context. Okay, so overall, this is what we are going to do. We're going to run log set analysis to obtain the candidate race set, right? And then for all accesses, we'll learn the feasibility prediction from the traces. And in each race pair, we are going to construct a candidate or hypothesis race trace, E star, that we believe will race, right? If the feasibility is high, then we pass on to actually try to reproduce the race. If the feasibility is 0 or low, we reorder the trace to try to make it higher, all right? So this kind of thing takes care of control flow and memory address dependencies. And if it's still too low, if we cannot find, make it higher after a few tries, we just drop it, okay? So that's the basic idea. Overall, we have this architecture. We have tracing in the Linux kernel. We have the Fourier coefficient estimation. We have the feasible race prediction. And then finally, the rest prediction checking, right? This is the component that we will use to finally predict the race, right? And remember, in all of this, the goal is to maximize the number of bugs we find for a given time, right? So you have to minimize the number of time the actual race prediction checking is invoked, right? Because that's kind of time consuming. All right, so in terms of evaluation, we evaluated, compared against our prior arc PLA as well as happens before. Remember, the complete happens before relationship is very high overhead, right? So of course it can, in theory, find everything, but like it takes a lot of time, right? So that's what we are kind of, we are baselining against. So this is kind of approximation of happens before, right? Because we only considered 2 levels of ordered pairs, and we put Fourier coefficients to approximate them, right? Happens before will, in theory, capture all of the dependencies, right? Anyway, so the bigger point is that it improves accuracy by 15.7% over PLA. In these graphs, you have on the x-axis the corpus size, and the y-axis you have the results, and it scales quite well with corpus size. Okay, it found many bugs across the subsystems. And the other thing to note is that, as I said, that the Fourier component of these traces are very sparse. Here are some numbers. You have along the x-axis the Fourier values, the ones that are non-zero, right? The count along the y-axis. The more condensed they are, the more sparse they are, right? So this is what we measured. And overall, in summary, we found that this approach that we talked about can approximate happens before relationship quite well for this kind of traces, and it customizes them. And in practice, it means significant improvement over just doing it over the stable set-based approach that we did before it. It found several new races. And I would also like to highlight the other aspect, that Fourier learning is a different form of learning. It's very efficient in terms of parameters, as long as sparsity is present. It explicitly uses sparsity. Of course, in the LLM world, there is also some speculation about using sparsity, but this is more tailored for sparsity exploitation. Thank you. That's all.
Hi. Sorry. Could you go into a bit more detail regarding you called it a hand-coded function for the features? Right. What features did you use there, and how did you make those choices? Thank you.
Right. That's a great question. The question is what kind of features we used. So the features were decided by the task at hand, right? So here our goal is to position. So we wanted to filter, and remember the traces, by taking the traces, we want to encode the features. So we primarily focus on instructions that can have any side effects in memory. So this will be read, write instructions, or some sort of mutex operations that has to do with synchronization primitives. So these are some of the example features.
Okay. Thank you for the talk. Just have a question. How did you confirm the data races that you found? Those 332.
Right.
Can you talk a bit about that?
Right. So what we did is, remember, as part of our analysis, we are trying to reproduce the race. So we have these sanitizers, right? So that kind of check whether a race is happening. We have the schedule as well. So we basically run the candidate traces with the schedule until we find a race. And only when we find a race, we say this is a confirmed race. And then we, of course, once we find them, we bin them and report them to the developers. And the developers also obviously confirm. Thank you. Thank you. Good catch. Sure, yeah, absolutely.
Is this thing on? Can you hear me? You hear me at the back? All good? Cool. Thank you. Nice.
Oh, yeah. Okay. So our next talk is going to be about mix testing, specifying and attesting ABI compatibility of C and C++ atomics implementations. And the talk will be given by Luke Geeson.
Thank you. Cool. You can hear me at the back okay? Is that all good? Yep, fantastic. Right. So I'm a PhD student at University College London. And together with my co-authors here, have been finding bugs in C and C++ compilers. So in particular, we're looking for concurrency bugs. I'm just going to get started and give you an example of what that might look like. So look at this example on the left. This is a test we used in a bug we reported in LLVM. It's what we call a litmus test. So it has a fixed initial state where x and y have initial values of 0. And then you have two threads of execution that read and write to these shared x and y variables. And then we have a question over the final state of running this program, which says, is there an outcome of executing these two threads from this fixed initial state where the local variables t and u both have the value 0 at the end? That is the wrong button. According to the C standards, so ISO C or C++, the answer is no. You should not observe that 0, 0 outcome. And this is because essentially ISO C has a chapter that specifies the allowed concurrency behavior of these atomic loads and stores. And that gives rise to the semantics of executions, that gives rise to the semantics of these final outcomes. So on the right here, this syntax is quite terse, but that is essentially a set of assignments to T and U. So each one of those is one of the possible outcomes allowed by C or C++. So that's your C program. So when you compile it, you would hope that you don't observe that 0, 0 outcome, right? And indeed, if you compile this to target ARMv7, you'll see that the assembly on the left, the pink stuff, is what is generated by LLVM. Now, note here that we have these things called DMBs. They're memory barriers. They prevent the effects of executing the loads or the stores before or after from reordering past this barrier. That, in effect, prevents the reordering, and it also prevents the 0, 0 outcome from occurring. So on the right, again, we have these three sets of outcomes, this time using assembly registers as opposed to local variables in C. But again, there's no 0, 0 outcome, so we're all good here. The important thing to note here is that the pink sequences are designed to work with the other pink sequences. They work in isolation. Also, if you compile this to target ARMv8, not ARMv7, you get the blue sequences. And in this case, instead of having that DMB fence, we have a STL and LDA instructions. So that's store, release, and load acquire. And the semantics of these are that they pair up together, and they basically form a release acquire barrier, if you will, that prevents the reordering and also prevents that 0, 0 outcome once again. So the important thing to note here is that with pink is designed to work with pink. Blue is designed to work with blue. However, if you mix them, you observe the 0, 0 outcome. And this is a mixing bug. This arises because the store release instruction and the LDR instruction, they don't synchronize. So the LDR does not have ordering semantics with respect to STL. Therefore, one can reorder past the other, giving rise to this 0, 0 outcome. This is a mixing bug. This is what we're looking for. This has been reported in LLVM. It's been triaged for fixing by engineers. We haven't fixed it yet. Got a few things to do first, but yeah, that's the kind of thing we're looking for. Concurrency bugs. So to give you a high level, to zoom out a bit and give you sort of the big picture, I guess, we're looking for behaviors of the compiled program under the architectural model or the implementation of the model, so a Raspberry Pi, that are not behaviors of the source program under the source model, which in this case is ISO C or C++. And we're comparing sets of outcomes, which we rewrite so that we can compare machine and source states by using the mappings in the compiler. As we've seen, each atomic operation, so a load or a store, can have one of multiple possible assembly sequences, one of multiple possible implementations. and they can be mixed. This perhaps isn't surprising. This is what linkers have done for years. This is what portable applications are designed to do. But the state of the art hasn't necessarily looked into this all that much. There are a few web pages here, but there's no sort of papers, as it were. So this is what we did, and this is what I'm going to talk to you about today. We have a technique called mix testing, which allows us to test whether these mappings to different assembly sequences are interoperable. That means they can work with others. And we have a tool called Atomic Mixer that implements this technique. I'll give you an example of some of the bugs we found. And yeah, we're also going to show you briefly a specification that we wrote with my colleagues in ARM's compiler teams to try and prevent some of these bugs from arising in compilers in practice. Because this is a testing paper, we want to provide a spec that we can then implement and test against. Cool. So this is how we found the bug. On the left, we have a fancy LaTeX diagram. What we essentially do is we take a source program S and we split it into its constituent operations. So in this case, I'm going to move now. We take the source program and we split it into its constituent loads and stores. And then we get a set of all the sort of atomic operations you're compiling. And then we apply to those each of the possible mappings. So in this case, the load and the store both have two possible mappings respectively. So in this case, a mapping is defined as you could call it a function from C or C++ atomics to your various assembly sequences. These are typically accessed via like compiler flags. So we compile each of those operations separately. And then we get sets of assembly sequences back for all of the permutations of the compiler under tests. And we combine them into a set C of all the possible combinations of the resultant program. And we show the example of the buggy test earlier. That's just one of the tests that's generated by this sort of this flow, this technique. Cool. So overall, the Atomic Mixer tool essentially implements that whole flow. So splitting, separate compilation, combining. And it takes the test as input and a set of profiles that you're checking, gives you back a set of assembly tests you can then run under some simulation or on hardware to see if you observe reordering bugs. Cool. So we have coined a new term called a mixing bug, which essentially arises when you do this kind of testing. So we call a mixing bug that arises if any of the compiled programs C exhibit a concurrency bug with respect to the source program S. So that's using the concurrency bug definition from before. However, we're going to lean on this a bit because it has a few implications for testing that I think are worth stating up front. The first one is that these bugs only arise when you mix implementations of atomics together. So the prior work essentially takes a whole program, compiles the whole thing using one compiler mapping, and gets one program back. These bugs arise when you mix multiple mappings, and therefore it's sort of strictly more general than the standard testing we've been doing for the last 20 years or so. Precisely, prior work takes one compiler profile and tests the whole program, whereas mixed testing takes multiple compiler profiles and is essentially testing multiple implementations and how they interact. And this unfortunately means that mixed testing is exponential. It's exponential in the number of atomic operations you're testing and the number of compiler profiles you're testing, which means you can't run this every day. You can't deploy this in CI. If LLVM changes 5 times a day, you need to run 10 million tests and do mixing on all of those 5 times a day. It's not feasible. So instead, you might do this when the atomics mappings change in a compiler, which is much less often, but still important. Cool. So that's the technique and the tool and these sort of mixing bugs. To give you an example of how some of these bugs arise, we've given you an overview here as well. So these bugs can arise when you mix together ISA versions like ARMv7 and ARMv8 or ARMv8 and ARMv8.1. And there's a running example there where we mix together ARMv7 and ARMv8 mappings. However, this can apply in other cases too. I should say, we're not mixing, say, like RISC-V and x86 codes. So we put some constraints on what we're actually mixing because it still needs to run on a CPU with a fixed instruction set at the end of the day. So this mixing is allowed, but you have to be careful about how you specify mixing. We also find bugs when you're mixing, say, GCC and LLVM implementations together. So one of the bug reports we have open is on atomic structs, where the size and alignment of structs in LLVM and GCC differ, which means one may write or load padding bits where the other one expects data, which means if you mix these together, the program will read nonsense. Some of these bugs have been fixed, some of them are still open. It's all work in progress. But yeah, I encourage you to check out the paper as well, because we've also reproduced sort of non-mixed testing bugs too, just to sort of show how one is a generalization of the other. And we prevented a mixing bug from arising in the JVM when one of ARM's partners asked about whether the mappings would be sound. Again, it wouldn't have arisen in normal circumstances. Cool. So I said mixed testing is exponential. We wrote a specification with our colleagues in the compiler team to try and bound the search base a bit, because yeah, each compiler implements a different set of mappings, and we want them all to be interoperable with respect to each other. So this is essentially 20 pages of the allowed mappings from C atomics down to ARMv8 assembly, in addition to special cases that compilers need to implement. In theory, if your compiler implements this spec and links against the program generated by another ABI compliant compiler, then you shouldn't observe any of these strange reorderings. Up to bounds on test size, of course. So I'm not making any verification or proof claims here. Yeah, I encourage you to check it out. I've also got a copy on my iPad later if anyone wants to have a look. That's about it. That's the technical stuff. Now this is a sort of formal PL testing audience, so some open questions here, like, does this apply to other architectures? This was the reply we got when we reported that atomic struct bug. Someone was asking what the x86 ABI says about all of this, to which the reply was, I've been asking for it to say something for years. So it's possible that this applies to other architectures. We don't know, we haven't looked. And also soundness. So when someone proposes like a C or C++ memory model, they typically provide with it a set of like idealized mappings down to each architecture. This is typically a one-to-one mapping. What we've sort of shown here is that compilers in practice actually have a one-to-many mapping. And so it'd be nice if someone does some multi-mapping soundness proofs. Very clear, easy idea, but probably is a lot of work to actually implement the thing. Cool. So that's the paper. There's an artifact as well if you want to have a look. And that's essentially it. We have a technique that mix tests compilers. We have a tool that implements this. We found some bugs, and we wrote a spec to try and outlaw the scalability problem that comes with mixing all of these implementations. Yeah, one more thing to ask of you. My co-author wrote a really cute little blog post. It's very accessible and easy. If you want an introduction to this kind of relaxed memory concurrency bug finding stuff we've been doing. Provides a bit more context, and also has some cute AI-generated bugs too. Thank you very much. I'm happy to take any questions.
Questions? Yeah, you can just step up to the mic.
Thank you for the talk. Maybe I just want to ask a clarifying question. Like, when you say this mix, you mean a compiler compiles to the binaries with a different target architect, or it's the same architect that you are compiling different part of the program, and then you link them together?
Yeah, so we are taking a program, we're splitting it up, and we're compiling it to target different versions of the same architecture. So ARMv8 and ARMv8.1 are different versions of the ARMv8 architecture. They're compatible, but you couldn't mix those with, say, RISC-V code. That wouldn't make sense.
Oh. So aren't they supposed to be the same instruction set? If it's the same architect with different wording, why is that would be the problem?
So it's the same instruction set, although each architecture version may have slightly different semantics for the same instruction. But it is fundamentally the same instruction set, just with new instructions or slightly different ones. At the end of the day, your program will be compiled, linked together, and it will run on a fixed machine, which will have a fixed semantics.
I see.
But you're going to be mixing a sequence here and a sequence there. The linker might combine them, and then you still may observe reorderings based on what that hardware actually implements from the model.
Okay.
Yeah.
Thanks.
Hi. Great work. Really enjoyed the talk.
Thank you.
These litmus tests are a bit fiddly, right? So if they trigger, clearly you found a bug.
Yep.
If they don't, maybe you missed it. So how do you know when to stop? And were there any litmus tests that are possible but so infrequent that you had to give up and not use them?
Yeah, it's a good question. I gave a CGO talk at the start of this year on addressing this problem, so it's very handy. The state of the art would run this on hardware loads of times, and you're given a high probability of observing bugs, but not guaranteed, right? So what we have here is we're essentially running all of our testing under a simulation of the C model and a simulation of the architecture model. So we're using the official ARM v8 AR64 model, which is encoded into an executable tool, which can essentially give you repeatable results. And they are designed to be reflecting of the ARM architecture reference manual. So they're as close as you can get to a ground truth. That's how we avoid this whole probabilistic problem. That was kind of previous work, and this is kind of the next step. Happy to talk about it later as well.
Follow up if I have time, real quick. How easy is it to use that simulator? Can I, not working at ARM and not being an ARM engineer, use it? Is it that easy? Or?
Yeah, there's a GUI for it, the web page.
Oh.
I'll send you a link later. Come and find me.
Please do. I'm working on something similar.
Awesome.
Thank you.
Thank you.
Okay, I had one question.
Sure.
So these are clearly bugs,
Yep.
clearly very nasty bugs. Did you all kind of discover this class of bugs, or is there some bug in the Clang bug tracker involving some horrible war story of someone who couldn't figure out what the heck was going on with their program, and eventually they tracked it down to this kind of bug with a mix of architectures due to some precompiled library, something like that? Do you have any examples of that, or you guys just thought of this?
As far as I can tell, I haven't seen any bug reports like this. I've seen sort of things on mailing lists that allude to problems like this, but I haven't seen someone explicitly write down, this is a mixing problem. This arises because of this. There is like a web page where I believe Peter Sewell tried to list some of the possible mappings that each architecture might have, but no one's really sat down and hashed out the idea, I guess. So I say we coin these things as mixing bugs. They're not necessarily surprising. Again, linkers have been around for a while, but yeah, I guess we're the first ones to write a paper on it. Again, if I'm wrong, I'm happy to be disproven, but yeah, as far as I know, yeah.
Very cool. Okay, let's thank the speaker again. Okay, so our next talk will be on practical verification of smart contracts using memory splitting, and the talk will be given by Chandra Nandi.
Thanks. Hi, everyone. So yeah, my name is Chandra, and today I'll be talking about some techniques that we've built for scaling formal verification of smart contracts to real-world programs. And this is work with my colleagues at Certora, Shelley Grossman, John Toman, Alexander Baxt, Samir Arora, and Muli Sagiv. So smart contracts, if you haven't heard of them, are these programs that are used for doing financial transactions. And often these programs are deployed on blockchains like Ethereum, Stellar, Solana, and so on. So because these programs are often dealing with financial transactions, bugs in these programs can have really severe consequences. And so in the past decade or so, numerous tools have been proposed that are finding bugs in these programs, verifying these programs, doing fuzzing, and so on. In fact, there are so many tools that now there are dozens and dozens of surveys of those tools, and more of these surveys might be coming. So this is a pretty crowded space with lots and lots of tools and lots of techniques that are proposed very often. But unfortunately, even though there are so many tools out there, it doesn't seem like they scale to verification of real-world programs, especially when verifying complex properties. And so in this talk, I'm going to present one particular technique that we have come up with. And this technique helps us scale the formal verification to real programs. And they're built as part of this tool called the Certura Prover that we've built. So the Certura Prover is an automated SMT-based verification tool. It works at the bytecode level. So it takes as input a program in a high-level language like Solidity, Rust these days, and some others like Viper. And it takes a specification, and it just generates a verification condition and sends it to SMT solvers and gets a result. So as I said, the tool works at the bytecode level. So if a tool has to work at the bytecode level, then the tool should be able to reason about memory. And because we are working with SMT solvers, this is actually really difficult because often what it boils down to is that the solvers often have to learn a bunch of invariants about objects that may be completely unrelated to each other. And so to understand what that means a little bit better, I'm going to actually first give you a little bit of a background on what EVM bytecode looks like, and in particular we'll focus a little bit on the memory aspect, and then I'm going to explain the problem and then propose our memory splitting transformation, and then finally show some results. Okay, so in the EVM, memory is basically laid out as a giant single array of bytes, and I should be clear that for the rest of this talk I'll focus on bytecode generated by Solidity compilers. So you can imagine other compilers generating other kinds of bytecode, but this is focusing on different versions of Solidity. So it's just a big array of bytes, and unlike other languages like JVM or maybe even C, there is no way of knowing where allocations are being made. So there's no malloc or new or anything like that. So how does allocation happen? So basically, there is a particular value called, called the free pointer. The free pointer lives in a particular slot in this memory, and it's always the slot number 64. And so anytime you need to do allocation, you read the value of the free pointer. It tells you where the next free slot is, and you can allocate your object there. So as you can see, this is pretty low level, and there are no techniques that are available that can be used to infer a bunch of these high-level abstractions that you can easily do if you have languages like C or Java with explicit allocation mechanisms. So to make this a little bit more concrete, let's look at a particular program. So here we have a contract. This is Solidity code. It has a contract called C, and there's a struct called streams, and it has two arrays. And so a few facts. The pointers are all 32 bytes. And the array itself has a size. And when memory is allocated for the array, the first element is actually not the first element of the array, but it's the size of the array, which is actually really nice. And so each of the elements themselves are 32 bytes. So in total, you need 32 plus 32 times the size of the array. And so just to give you a visualization of this, so essentially what happens is, as I was saying, the free pointer is always at index 64. In hex, it's just 40. And you can see that the struct is made of two of those arrays, K1 and K2, and the first element of both of those is the size. And then ultimately, once the allocation is done, the free pointer is going to point to whatever is available at the end of the second array of the struct. Okay, so that's how memory works in this for EVM. So what's the problem? The problem here is that if the solvers, when you generate the verification condition from the bytecode, the solvers will have to figure out if different operations in the bytecode are referring to different objects or are different addresses, or if those addresses can be aliased or not. So this is fine, actually, but the problem is that when you're dealing with real programs, you're going to have lots of reads and writes, and that will usually lead the SMT solvers to timeout. Or the alternative is that the SMT solver can just assume anything can alias with anything, but then you're going to have imprecise results. So what exactly happens when we actually generate the verification condition? So here I have a very simple example. mstore just means memory store, right? So it's just a store operation. We are storing x at location j and y at I, and we're just reading from g. And so when we generate the SMT queries, it's going to look something like this, right? So each of those m stores are going to get converted into these if then else expressions. So basically, when you load the value from g, we're going to first check if I is equal to g, then we're going to return y. Otherwise, if it's equal to j, then we're going to return x. Otherwise, we'll havoc. And these are all following from the read-over-write axioms. So as you can imagine, this is going to grow in the number of accesses to memory. And so that's not really very good. So what we propose is we want to simplify the program before we generate the verification condition so that we don't have so many branches. So if this is what we have before, then ideally what we want is to be able to cut as many of these branches as possible so that we have a simpler query in the end. But how can we actually figure these things out? How can we simplify it? Well, the only way to do that is if you can somehow figure out that some of these addresses are not going to be aliased, right? So if you know that I and G are not the same, then you can actually remove it. So how do we do that? Well, first, to be able to do this kind of simplification, you need some kind of program analysis, right? Otherwise it won't be sound. So we're going to build a program analysis, but the problem with that is, as I said, everything is based on this reading of the free pointer. So in order to build an analysis, we first have to know where allocations are even happening. So we have an analysis. It is made of these 3 parts. The first part is an allocation analysis. What this does is it basically tries to figure out where allocation is happening. So it detects where objects are allocated. The results of that are sent into an initialization analysis. And this analysis checks that any object that has been just allocated is actually initialized before it's read from. And then finally, we have a pointer analysis. It essentially points, maps pointers to sets of abstract locations. For the rest of this talk, I'll actually mainly focus on the allocation analysis. You can read about the rest of the analysis in the paper. The reason I focus on this one is because if you don't have this, then the rest of the system doesn't work. And it's important to have the allocation analysis first. OK, so let's remind ourselves what we want to do. So the goal here is to detect new allocations. And remember that the only way to get a pointer is by reading the value of the free pointer, OK, that lives in that slot 64 in memory. So the first thing that comes to mind is, OK, well, what if we just treat every read of the free pointer as a new allocation? Seems like something we can try. So let's try that. So here we have A equal FP and B equal FP. So these are clearly aliased, so this is not going to work. So let's try something else. What if we try to use an SSA numbering? So what that means is that every read is going to get a new, like a fresh incarnation number. So in this example, this seems to work, actually, because there are no interleaving writes. So both A equal FP and B equal FP will have the same incarnation number. And so the analysis will say that A and B may alias. That's good. But this is actually not quite right. So the problem happens if you have some kind of condition in between those 2 lines. So say you have A equal FP, and you have some condition inside which the free pointer can be updated, and then you read the value of free pointer again. So because of SSA, the 2 reads are clearly going to have different incarnation numbers. But if you don't take that branch, they may still be aliased, right? So this is not right either. So instead, what the allocation analysis actually does is it actually does do the SSA incarnation thing. But in addition, it checks a property of the program. And if the program does not satisfy the property, then the analysis will fail and say that this program seems weird. So the property is called the definite write property. And so what it says, effectively what it says is, if you read the free pointer, you better update it after that read. And so more formally, it says that a read under some incarnation I must reach an update of the free pointer without any interleaving updates of the free pointer. So going back to that program that we saw, so here we have the read of the free pointer at location B, so at B equals FP. We can't say for sure that it's updated because it does not satisfy that, because if the condition is false, then the branch won't be taken, and so this update will not happen. And because of the fact that this definite right property is violated, the analysis is going to fail and say that, well, this program doesn't satisfy the property. However, if you did have an update of the free pointer before the condition, things would be fine, right? Because we know for sure that FP has been updated, so A and B will have different incarnation numbers, but at the same time, it also means that we can confidently say that A and B are not going to be aliasing. One other thing about the allocation analysis, so if you actually move that free pointer update from before the if to the after the if, this is actually also going to fail. So the analysis does not like this, and that's for a different reason. So it's necessary for the free pointer's value to be always increasing. And if you have the free pointer update at the end of that condition, it's possible that somebody can actually reduce the value of the free pointer, and that's going to break a bunch of invariants. So the allocation analysis is not going to allow this. So overall, in summary, the allocation analysis essentially assigns these abstract locations to different free pointer reads by using this idea of this SSA incarnation number. In addition, it checks a couple of other properties. So the first property is it checks that the program satisfies this definite right property. It also checks that the free pointer's value is strictly increasing. And another thing it does, and I didn't get to it at all this time, is it does some lightweight pattern matching over the program itself to infer the shape of the object that was allocated. So it can detect if it's a struct or if it's an array or something like that. And as I said, the remaining analyses are in the paper. The paper has quite a bit more. So if you're interested in the Greek, it's in the paper as well. And there's also some coverage of related work. So there are some other papers, in fact, that have done analysis over Ethereum memory. So if you're interested in those, we discussed those in the paper. I now want to go back to the original problem that we started with. So remember, our problem was that we wanted to speed up SMT solving. So from that, we somehow went to this program analysis. So why did we do any of this? The reason is that we want to be able to simplify programs, and we want to do it soundly, right? So the analysis is designed so that we can simplify the program before we generate the SMT queries. And so here, I'm not expecting you to read the code on the right. That's just a representation of the bytecode that we work with. But the highlighted parts show what exactly happens at the end of all that analysis and everything, right? So you can see that on the left, there is a single array called mem. And after the analysis is done, you can actually rewrite the program to use different arrays for objects that you know are definitely disjoint objects. And so the consequence of this is that ultimately, when we generate our queries in SMTlib, we have fewer branches in the IT expressions. OK, so now I want to talk about some results. So our goal was to, again, speed up SMT solving when doing formal verification. So to evaluate the system, we took 229 real-world benchmarks, and we ran formal verification on them with and without the memory splitting transformation. And so each of these benchmarks is actually a verification task, which means that there is a program in Solidity and a corresponding specification that comes with it. And so we ran our verification tool on those. And so points above the red line are good. So you can see here that in many cases, we are able to speed up SMT solving. But the most notable result is the number of timeouts that we solved. So the Surtra Prover is actually an industry scale tool. We have people who come to us with their code and want us to verify it. You can't tell them that our solver timed out, so we can't prove your property. So it's really important for us to be able to resolve these kinds of timeouts. And so the fact that the analysis and the transformation helps with that is really, really important. There's more in the paper. So we discuss how the benchmarks were selected. The paper also reports on the total number of partitions we were able to produce for each of these benchmarks. So remember, we are breaking down a big array into smaller arrays. So how many of those splits are happening, that's reported. We also have a comparison in the paper with another tool called Helmus. So Helmus is another verification tool people use for checking high-level properties of smart contracts. And so we compared against that as well. And finally, here's an interesting side effect of all the work that we've done. We did not expect this to happen. But turns out that because we implemented all this analysis, we were actually able to find a bunch of bugs in Solidity compilers. Our goal was never to go looking for bugs. But because we built the analysis and we have this trust but verify approach, where we verify whatever the Solidity compiler says it's doing, we were able to find a bunch of violations of some properties, and we reported them to the Solidity team, and they've all been acknowledged and fixed. So that's my talk. So we presented a memory splitting transformation that speeds up SMT solving, applied to smart contract verification, and we also found some interesting bugs in compilers. Thank you.
Hey, thanks for the talk. My question might be naive. So I guess like how general this approach is, like the Solidity increase the free pointer, but what if for the other types of memory management systems, like do you provide other types of optimization there?
Yeah, so I think the question is how common is it for the memory to be allocated this way, bumping the free pointer, right? And if we support other memory allocations. So for Solidity is one of the most popular languages that are used in this space, and every version of Solidity, like this is how they do it, right? So it would be surprising if this suddenly changes, or if suddenly they decide that they're going to do something else. We support from like some of the oldest versions of Solidity, like 4.2 or something, up until the most recent ones. And this seems to be applicable to pretty much all of them. We actually also support Viper. So Viper is another language that generates Ethereum bytecode. But I'm not actually sure how they're, if they use the same mechanism.
Yeah, so the goal of your analysis is to separate the monolithic memory into different memory objects.
Yes.
And the reason why it works in C is that if you have a pointer to a specific memory object and you do a buffer overflow, you will not point to another memory object because it will be an undefined behavior.
Mm-hmm.
And you don't have this property in your virtual machine. And so I was wondering how you deal with this issue.
So if the free pointer's value overflows, is that the question?
Yeah, if you have a pointer to a memory object that was allocated and you have a possible buffer overflow, then you'll be pointing to another object, which is valid in the low-level semantics that you have, where it will be a undefined behavior and a buffer overflow in C. And so how do you account for this problem?
So the question is, if the increase of the free pointer is now suddenly part of the allocation of a different object, so how do we?
I think the question is about whether you could read from the free pointer and then do pointer arithmetic. So all of a sudden you're going to be pointing to a different object or something like that.
Yeah, exactly.
So you can do that. I think we strictly are always analyzing code that is generated by the Solidity compiler, and the compiler-generated code will likely not do this. Okay. But it's possible that inline, in this space, it's actually possible for people to manually modify the free pointer and do arithmetic on top of that. I think that we will probably not be able to handle that.
Okay, thank you.
Yeah.
Hey, great work. So I wanted to ask something regarding the compiler bugs you found. Were you able to have to run analysis that were able to find the impact of these bugs in real-world contracts, like at scale? Was it something that's easy?
So this happened in not actually in bugs that I showed in the table, but as I mentioned, there's other compilers, like there's the Viper compiler, which is, Viper is another language. And we actually found a bug in, well, there was a known bug in the Viper compiler that did lead to some very severe consequences in the DeFi space.
Yes.
We didn't find it because of this analysis, but it's definitely possible that these bugs do have real-world consequences. Our bugs were fixed before they were exploited, so hopefully, nobody suffered from them.
Okay, thank you.
Okay. our next talk, I believe, is for a distinguished paper. This is a talk on fast and optimal extraction for sparse equality graphs, and the speaker will be Chun Kit Lam.
Good afternoon, everyone. I'm Chun Kit Lam from HKUST, and this talk will be about fast and optimal extraction for sparse equality graphs. So before diving into the technical details, we should first explain what is an E-graph. So basically, an E-graph is a graph plus some equivalence relation over the vertices. So consider the following expression, 2 divided by a times 2. The initial E-graph is basically just an expression graph. So as you can see, this is very similar to an AST, except that for the node 2, we somehow merge them together. So in a normal AST, you expect the node 2 to be duplicated, so you should have 2 copies. But for an E-graph, we merge those that are equivalents together so we can have a more compact representation. And for optimization purposes, people often apply rewriting rules to the equivalence graphs. So for example, in this case, we can rewrite the 2 multiplied by a into a left shift by 1 bit. And the dotted lines here represent that the 2 vertices inside are equivalent. So a times 2 is equivalent to a left shift by 1. So this is the basic idea of E-graph. And equality saturation workflow basically says that we apply those rewriting rules, which is what is called elaboration, until we can no longer find new results by applying those rewriting rules. So this is called saturation. And after this elaboration, we try to extract the optimal term that is the same as our target input term. And with this, we can get the optimal result with respect to the rewriting rules. And this framework is adopted by CraneLift, a JIT compiler for optimization, and there are also many applications using the recent egg library. However, there are 2 caveats with respect to this optimality result. So first, we need to elaborate until saturation. But this may not be feasible in some cases where the graph is large or the rewriting rules are very complicated. And in the second case, we must use optimal extraction in order to get the optimal results. But this optimal extraction problem is actually very hard. Like NP hard to even approximate to a constant factor. So people usually just use heuristics or try to send the question to integer linear programming solver and hope that we can get the optimal results within certain timeouts. In our paper, our contribution is to propose the first fixed parameter tractable optimal extraction algorithm. So it does 2 things. So when the graph is sparse, we can get the optimal extraction in a relatively short amount of time. And the second thing is because we can have certain estimates of the sparsity of the graph, we can see if the graph if it is not sparse, we know definitely that our algorithm will not work quickly. But if the parameter is small, we know that it will definitely solve the problem really fast, and there's no need to guess the runtime of the algorithm. So before getting into the details, we first have to change the encoding of the E-graph a bit, because as a graph with equality relations, it is a bit hard to parameterize. So we formulate it as a bipartite graph. So we transform it into directed bipartite graph with E classes and E nodes. So the nodes here are the E nodes, which corresponds to the solid boxes here. And these circles are E classes. For each E class, it can point to multiple different E nodes. For example, this C3 points to the multiplication and the left shift operator. And this means that these 2 are the same, so they are in the same E class. And a set of vertices S is a valid extraction result if for every E node inside this S, we capture all its dependencies. And for every E class, we contain at least 1 member of it. So consider this the example on the left-hand side. If we extract these 3 vertices, this is not a valid extraction result, because for the left shift operator, we didn't extract these 2 E classes, even though two members of the E classes are extracted. And in the middle case, this is also invalid because for the E class C5, we didn't extract any of its member, which is A. And in the third case, even though there is no E class associated with the vertex 1, this is still considered valid extraction results according to our formulation. And the optimal extraction problem is to find some valid extraction results that contains the roots E classes with the minimal cost. The roots E classes means that you want to extract something that is equivalent to your input expression. And this problem is NP hard to even approximate. This can be shown by reduction from the set cover problem. So you can convert this set cover problem into an E-graph extraction problem with unit cost. And this is so this shows that E-graph extraction can be really hard. And when it is NP hard, we want to only solve it for some families of graph. And because we already have optimal extraction algorithm for trees, so if we don't consider the cost of sharing, we already have fast optimal extraction algorithms. So the natural choice is to use tree width. So it measures the tree likeness of your graph. And in this case, the parameter tree width, when it is small, it means that the graph is sparse. So tree width is defined using tree decomposition. So consider this original graph. We can have the tree decomposition of that graph. A tree decomposition is basically a tree where each node maps to a set of vertices in the original graph. And this tree decomposition has to satisfy certain properties. For example, for every edge in the original graph, say this C1 points to the division operator, both endpoints must reside on some set in the tree decomposition. For example, this one. So both C1 and division are inside this node. And the second requirement is that for every vertex containing the vertex in the original graph, so for example, if we consider this C2, so these four nodes in the tree decomposition node contain C2, so they must form a connected component. And this is what makes tree decomposition powerful, because in the sense that we can have a cut property where we only have to consider things in the current bag. And to simplify things further, we consider a nice tree decomposition where we only have 4 kinds of different nodes instead of a general tree decomposition. But in a nice tree decomposition, the size is also linear to the size of the original graph. So we have, say, the empty node, where the set of vertices is empty. And we have this introduced node, where we introduce an additional vertex comparing to the child of the current node. And then we have forget. So we minus 1 vertex from the child. And at the end, we have join node, but we will not talk about here due to time limits. And our algorithm is actually very simple. We track valid partial solutions that are valid in the explored subgraph. So in our dynamic programming, we compute the set of valid partial solutions bottom up in the nice tree decomposition. So we start from B1 and then work our way up. And then for join nodes, we will somehow do subset convolution to join things together. This valid partial solution for E nodes, we must make sure that the solution contains all dependencies of that node. So this is quite similar to the valid extraction definition before. But for E classes, we do not require the solution to contain a member of that E class for now. So for example, if we consider the set of valid partial solutions for up to B4, so it means that we consider a subgraph containing 1 and C4. These 4 are all valid partial solutions. Even though for this solution containing only C4, we do not have the member, which is 1. But this is still considered valid for now. And then when we encounter an introduced node during our dynamic programming, we just copy all those valid partial solutions and add the introduced vertex to it. And then we try to remove those that that are now invalid. So for example, starting from B4, we have these 4 valid partial solutions, and then we try to add the newly introduced left shift operator into each of the solution. But some of them can be invalid, so we will remove them. For example, if we consider only a solution containing only the left shift operator, because C4 is also in the explored subgraph. So the solution containing only C4, only left shift is not valid. So it is not present in this set of valid partial solutions. And note that solutions can become invalid after introducing more vertices. So we cannot just check the newly introduced solutions. We have to check them all. And for forget nodes, we check that if we are now forgetting an E-class C, it must be satisfied now. So it means that we must contain its member if we want to extract that E-class. The idea is that in a valid tree decomposition, when we forget the E-class C, we know that we will not introduce its neighbors because all its neighbors should be added before. And so if it is not satisfied now, so if we don't have the member, we will never have, it will never be satisfied later, so we can just throw the solution away. And for the optimality and complexity, it seems that this partial solution set size grows exponentially because we are just always duplicating those solutions. But it turns out we don't have to track all of the valid partial solutions if our cost function is nice. So this requirement is monotonicity, and for things like positive cost summation cost, it is monotonic. So we don't have to track all the valid partial solutions. For example, for the set of partial solutions for B4, it turns out we only have to store 3 of them instead of 4 of them. And in general, the size is bounded by 3 to the tree width, where the tree width is the size of these bags, the maximal size. And this is much better than just having the 2 to the power of n, which is exponential. And typically, when we consider some small tree width, for example, at most 10, this complexity is really good. So essentially, these terms are pretty small constants, and they are and the complexity becomes linear when the tree width is small. So we implemented this in crane lift for experiment. So we want to see if E-graphs in crane lift have small tree width, and because E-graphs in crane lift are cyclic, we can apply our algorithm. And for benchmarks inside egg, so for the extraction gym, they require a cyclic extraction, which is a slightly harder problem. And we compared our results against the CBC ILP solver, and we also compared against Gyrobi, which is a commercial integer linear programming solver, to see if our algorithm is much faster than just trying to do ILP. And it turns out that in our benchmark, most of the E-graphs have tree width at most 10. And if you only consider E-graphs that are a bit bigger, so they are less trivial, still 94% of them have tree width at most 10. So this means that our assumption works for the crane lift case. And in 96% of the instances where the tree width is less than or equals to 10, our algorithm is significantly faster than integer linear programming solver. And it turns out the bottleneck of our algorithm is not really in our FPT algorithm, but it is in the heuristic to get the tree decomposition. So if we don't consider the part that computes the tree decomposition, because there can be many ways to do that, our algorithm is like 10 times faster than integer linear programming solver. So we have some possible future works. So because tree width may be too big for some applications. For example, when we check the extraction gym for doing extraction with the egg library, we found that the tree width can often be 40-something, which is a bit too big for this algorithm. So maybe there can be some alternative parameters. And also, a cyclic extraction is still unsolved. So we can actually generalize this algorithm to give us a still FPT algorithm for a cyclic extraction. But this requires double exponential on the tree width, which is not very practical. And also, we would like to see if there are some heuristics that can be used to improve our performance. So for example, currently, tree decomposition libraries often try to get a much smaller tree width. But it turns out in our algorithm, as long as the tree width is, say, more than 10, you really don't need to optimize it further. So it's interesting to see if there are ways to get a faster tree decomposition or some other algorithms to do, say, fast subset convolution, because our runtime is actually dominated by the join nodes. So that's the end. I'm happy to take any questions.
Questions?
Hi. I wanted to ask if you have some results in cases where the cost function is less nice, you called it that.
Yeah.
And yeah, if you could explore for a bit, or expand on that a bit. Thank you.
Yeah, so basically the requirements of that nice cost function is that we have to make sure that the empty extraction result is cheaper than everything else. So if you extract something, it should cost more than extracting nothing. And the second requirement is if you add some vertices and it is not present in the original two solutions, it should preserve that order. But that notion is a bit complicated, but we mentioned it in the paper. So maybe you can see if the formulation works.
Hi, thanks for the talk and congrats on the award. Did you run this on any of the systems that use equality saturation, like end-to-end, to see if you're able to extract like an optimal program from one of the tools that have been built in the past years that use equality saturation?
Yeah, we actually only tested it with crane lift because for benchmarks using egg, I think they often require getting that acyclic extraction, but that is much harder. And in crane lift, we kind of avoided this problem because their E-graph are already acyclic.
Yeah.
So no.
Right. Okay, thanks.
Thank you very much for the talk. My question is sort of about, like you compared in the evaluation, your solver to like the ILP solver.
Yes.
But I'm actually curious to know sort of like how much more optimal are these optimal answers than sort of the quick and dirty ones? For example, if you had an extractor that was just going by like assuming tree width of 1, so this is the optimal like tree extractor, assuming that the answer is going to be a tree, how much worse do the results degrade if you have like a tree width of 10?
Yeah, I think we just implemented something with crane lift where we found the size. So we were trying to like minimize the size of the final code, and I think we got like 2 to 3%, which is not a lot. But there's also another problem with the architecture of crane lift. So they are so in their code they are kind of assuming there's no sharing. So they implicitly assume that because they try to compute the optimal extraction cost for every single E-classes. And in that sense, you can't have any sharing because they sum them up later. So there's some improvement, but we expect like a bit more improvement if that thing is fixed.
Thank you.
Okay, let's thank the speaker again. Okay. The final talk for the session will be on hybrid SA, GPU acceleration of multi-pattern regex matching using bit parallelism. And the talk will be given by Alexis.
Thank you for the introduction. So I would like to present to you our latest work, which is a GPU-CPU heterogeneous engine for multi-pattern matching. So first, let's talk about the regular expression. So in general, when we talk about regular expression, there are three kinds of operators that we have in mind, which are the concatenation, union of clean star. But we also encounter in real-world regular expression other operators that are regular, like bounded repetition, look around, or not, like back references. The general approach when we want to do matching of a regular expression into first transform it into an equivalent automaton, and more particularly into a non-deterministic finite automaton. In our work, we use the Glushkov construct to do this because it has a neat property that is useful for bit parallelism that is called homogeneity. So here is an example of an homogeneous automaton. What you can see is that for every state, if you look at the incoming edges, they're labeled by character class. They all have the same character class at their incoming edges. For instance, state Q2 has character class BC as incoming edges for both the self loop and the loop and the edge coming from state Q0. Therefore, what we can do is instead of labeling the edges, we label the states. And this is going to be useful later on. And we also represent the final states like here with this representation. So the key computational problem that we want to solve in this work is the multi-pattern matching problem. So what we have is a set of regular expressions, and we want to find the occurrences of those regular expressions over an input text. So first, let's talk a bit about the GPU programming model to understand how we can do NFA simulation on the GPU. So it is often referred to as single instruction, multiple threads, because we have many threads that must execute at each step the same instruction. There are several problems that can occur when you create a program on the GPU. The first one is called divergence, because sometimes you might have two threads that are going to execute different instructions. Another thing is when you have threads that must communicate, you have to synchronize their shared variables to have a consistent value. Another thing to keep in mind is data locality, because you would like threads to have coalesce memory access to use the cache instead of the global memory that is much slower to access. So on the GPU, the typical way to do NFA simulation is as follows. You have a set of threads, like here I showed thread 0 up to 3, and each state is assigned each thread is assigned a different state. For instance, here state Q0 is assigned to thread 0, state Q1 is assigned to thread 1. And what is going to happen is we have here the pseudocode for NFA simulation that is going to be executed by each of those threads. And what happens is we're going to iterate over the inputs. And at each step, what we're going to do is first activate the initial states. We're going to have a synchronization to have a consistent value for the next bit vector. And then every thread is going to check if its state is active or not, and then going to iterate over its successors. And if the successor label matches the current character, then we're going to set the bit as the position of the successor. And then we update the active state. So there are several issues if we want to port that algorithm to the GPU. The first one is you have a lot of synchronization at step 3 and 8 that can slow down the performance. Another thing is if you look at those highlighted in purple between line 4 and 6, you have a lot of branching because some of the threads might take the branching and some might not. For instance, at line 5 here, we're iterating over the successor of a given state. So if you look at thread 0, it is responsible for the state Q0 that has two successors that are Q1 and Q2, whereas thread 1, responsible for state Q1, has no successor here. So thread 0 is going to have more work to perform than thread 1, which can result in imbalance. So those are the two main issues. As I said, the most existing GPU regex engines, they use a variant of this algorithm that I just showed you. And this can give rise to divergence and requires synchronization. So the main issue of divergence is that it can lead to the serialization of the instruction execution and therefore can reduce the throughput. The thing is, GPUs are actually good when you have the same instruction to be executed by different threads over multiple data. This is why in our work, we focused on bit parallel algorithms such as the classical shift-and because we think it's a good fit to support certain classes of regular expression that have simple transition patterns on the GPU. So first, let's introduce the shift-and algorithm on this regular expression here. So we represent the NFA that is created by the Glushkov construct here, and below we have the active states. And the first idea of the shift-and algorithm is that the active states are going to be encoded in a register. And here the register is going to be of size 4. And if state QI is active, then we're going to set the ith bit starting from the right as at 1. Like for instance here, state Q0 is activated after reading letter A in the input ACD, so we put a 1 below it. The other idea of the shift-and algorithm is that we're going to be able to simulate the NFA only using bit parallel instructions that are bitwise OR, bitwise AND, and shift left. So let's go through a series of instructions to simulate the NFA here when we consume letter C. So first, we're going to simulate the transition by performing a shift left by 1, activating state Q1 and deactivating state Q0 here. Then, because the initial states are always active, we're going to activate the initial state using a bitwise OR here. Then, we only keep the active states that are matching the current character, here, letter C. This is why we are deactivating state Q0. And finally, to compute the output and check if there is a match, what we do is we compute the intersection between the set of active states and the set of final states. Here, because Q1 is the only active state, but it's not a final state, we don't report a match. And this operation is performed with a bitwise AND. So this algorithm has several advantages if you compare it to the algorithm I presented before, the standard NFA simulation. The first one is one thread, instead of simulating only one NFA state, is going to simulate one NFA at a time. And this solves many problems that we had before. The first one is you don't need communication between the threads because NFAs are independent, therefore no synchronization. Another problem that is solved is about divergence. Before you had this for loop to iterate over the successors, to take all the transitions. No, because we're only using one instruction, a shift left, to perform the transitions, we don't have divergence anymore. There are still some limitation of this algorithm. For instance, it can only simulate transition of the form state QI to state QI plus 1 that look like a line. Moreover, there is also a restriction on the number of NFA states that must be at most the size of the register. And this is indeed a restriction. There are many regexes in the real world that look like this one here, AB02C. And here I colored in different colors the transition with different distances. So in red, there are the transition of distance 1 that we could support with shift-and. But the transition of distance 2 and 3, we cannot support them with shift-and. So the question that we want to solve is, can we extend this shift-and on the GPU to accelerate most regexes on the GPU? And the answer of this paper is yes. We propose extensions of shift-and and rewritings that enable us to accelerate about 80% of the regexes on our data sets over the GPU. And the main idea that we have is to use an heterogeneous approach using the CPU and the GPU to accelerate the vast majority of regexes on the GPU and run concurrently the rest on the CPU. So this is how our architecture looks like. We have a set of regexes here in blue. And what we're going to do is, during a compilation step, we're going to split them between the GPU and the CPU. On the GPU, we have several specialized kernels, about 80 of them, that are running concurrently, such as the classical shift-and or shift-and dis, which is an extension of shift-and to larger distances. On the CPU, we're running multiple instances of Hyperscan, which is a state-of-the-art CPU engine, one per CPU core. And so during this compilation step, we must choose whether the regex is going to go on the GPU or on the CPU, and for the GPU, which kernel we're going to use. So we're going to see now how we perform this compilation of the regex set. So we have many extensions of shift-and that we call kernels that are used to support regexes on the GPU. For a given regex, what we're going to do is we're going to choose the cheapest kernel that can execute this regex. How do we know which one is the cheapest? It's because one property of shift-and is that it's input independent because it doesn't depend on the active states. So we know exactly what the performance is going to be like. And on the right here, you can see a plot of the throughput in function of both the distance of the transition, the maximum distance, and the register size. As expected, the throughput decreases when you increase the register size or the maximum transition distance. And we also have rewriting rules that are going to help us later on to move a regex to a cheaper kernel that we'll present later. Another question is, how do we choose if a regex should be executed on the GPU or on the CPU? To perform this operation, we have a greedy algorithm that is going to start by the cheapest kernel only. And every time we're going to check what is the performance of the global algorithm. And we're going to keep adding more and more kernels until the load between the CPU and the GPU is balanced because they're run in parallel. Once we found that point, we're going to record the set of kernels and use it to split the regexes. And by that, I mean all the regexes that are supported by this set of kernels go to the GPU, and the rest goes to the CPU. Now let's talk a bit more about the rewrite rules that we use. The first one is called the distributivity rewrite rule. The main idea is to distribute the union of our concatenation to reduce the maximum transition distance. Here we have this NFA, and as you can see, the transition with the longest distance is the one in red here that is of distance 4, and we would like to reduce this. So what we're going to do is we're going to duplicate those orange states here and create 2 lines instead of this complex structure. And by doing that, we're able to reduce the maximum transition distance from 4 to 2. And so the benefit of this approach is, first, it can help us to move a regex from an expensive kernel to a cheaper one, or even a regex that was previously executed on the CPU could be executed on the GPU. It is, however, a trade-off because we lower the maximum distance, but by doing that, we had to duplicate the states in orange here. A second rewrite rule that we use is called the bounded repetition rewrite rules. There are many regexes that use this operator, bounded repetition, and we use this identity here that you can see to reduce the transition distance again. So what we do is we're going to split this transition of distance 3 into 2 transition of distance 2 here in blue. And again, this allows us to reduce the maximum transition distance from 3 to 2, and it can actually be generalized to all bounded repetitions. Now, I would like to present the experimental result that we have for hybrid assay. So we have considered many application benchmarks ranging from virus signatures to bioinformatics with brought-in motifs. And first, what we observe is that using our strategy, most of the regexes for the split are executed on the GPU, about 80% of them for most of the data sets. Then if we look at the choice of kernels that are executed in hybrid assay, we notice that for this ProSite and Yara dataset that have generally simpler regexes, the classical shift-hand is enough to execute most of the regexes on the GPU. But this is not the case for more complex datasets, such as Snort, Spam Assassin, and Suricata. And for those, we can see that there is more diversity in the kernels that are executed on the GPU, because there are more regular expressions that are larger, so you need a bigger register size, 64 bits or 128, and there are also longer transitions there. We have performed a comparison against a state-of-the-art engine on the CPU that is called Hyperscan and a state-of-the-art engine on the GPU, which is called OOPSLA, as well as a combination of the two, because we're using both the CPU and the GPU. So to have a fair comparison, we created a hybrid engines and 2 versions of it. One that uses the same split of the regexes as hybrid assay, and another one that uses a training step to improve the throughput. What we observe on this plot here, plus the throughput normalized to hot start, what we observe is that hybrid assay is actually consistently faster than all the other state-of-the-art engine that we've compared it to. Compared to one of the state-of-the-art GPU engine that is hot start, we have a speedup that is about 30 times to 200 times. And we also observe that the rewriting rules, so this is hybrid assay opt here on the plot, are actually useful for the more complex datasets, such as Suricata, Spam Assassin, and Levenstein, bringing higher throughput. So to summarize, what we've shown here with this work is that the bit parallel algorithms are actually a good fit for GPU execution. And instead of a full CPU or GPU engine, a heterogeneous CPU-GPU engine enables us to accelerate most of the regexes on the GPU, while the ones that cannot be efficiently executed on the GPU can be executed on the CPU. We also see that the rewrite rules help improve the performance, and our implementation has good performance against the state-of-the-art engine on the CPU and the GPU. Thank you.
Questions?
Hi, thank you for your talk. It was great. So I have a question that did you consider any CPU optimization in your implementation, like the SIMD instruction or any parallelization in the CPU side based on your implementation of GPU?
In this work on the CPU, we kept it to just parallelizing hyperscan. We didn't do more optimization on that side. We focused more on the GPU end.
And also, I have another question, if it's possible to ask. So, how do you handle the data transfer problem usually that is happening in GPUs? I mean, did you consider it in the choosing between CPU and GPU? For example, for large regexes, you prefer to put it in the CPU instead of transferring it to the GPU. Did you consider this or no? It wasn't a challenge.
So if I understood the question well, is did we consider for larger regexes whether we should execute them on the GPU or on the CPU?
Yep.
Yes, so we did that. So maybe I can go back a bit. Where is it? So actually here. So we have several kernels where we increase the register size. So basically the register size is analogous to the size of the regex, because if you have less than 128 states, for instance, we need a register size of 128 or something like this. So yeah, here we limit ourselves to 256 because we notice that after this, the throughput is so low that it's not worth it to use it on the GPU. So those regular expressions that are too large are going to be executed on the CPU because it's easier for.
Thank you.
Sure.
Question?
Hello. Awesome talk. Did you can you comment anything about the how much the thread divergence has reduced in terms of the before the optimization and after the optimization? Any comment about that?
So the question is about how the optimizations are used, or
how did the thread divergence change? How much has it reduced, or
okay. So actually, no, there is no divergence at all compared to the previous work that had this NFA simulation algorithm that I showed, a variant of it. So for us, because we use those bit parallel operation, we don't have divergence at all. This is the main advantage of it.
Oh, I see. Thank you.
Sure. And same for synchronization. It was also part of the question.
Yeah, I had one last question.
Okay.
Did you do any experiments to see how robust your speedups are across different CPU models or GPU models?
We focused on an Intel CPU. We didn't do it, but it would be interesting to see that. For the GPU, though, we tried on different instances, and what we observe is that because we have a lot of parallelism, so here those results are actually on GPUs that you can run. It's not like a server's GPU. So if you had a server GPU, the throughput would be much higher because the parallelism that we have is, right now we're limited by the hardware in terms of the number of total threads that you can execute simultaneously. So it would be even larger, and the speed up against the CPU would be larger as well.
Very cool. Okay, let's thank the speaker again.
you're 13 minutes in, so 2 minutes left. I'll give you 2, then I'll tell you when, if you get that far.
Okay, sounds good.
Yep, okay. All right, welcome everyone to our next session. We've got 5 great papers for you. First up, we have JMVX, multi-version execution for managed languages, and David is giving the talk.
All right, can you hear me okay? Sweet. All right, let's jump into it. I'm going to start by talking about the record replay parts of our system, and I'll loop back over to how multi-version execution connects to it, and I'll explain everything as we go. So I'm going to start by showing some code to you. This is Java code. It's going to read in or make a stream to a config file and do some work over it, process it, and attempt to do something. And I'm going to tell a tale of 2 perspectives, one a user, one a developer. So a user can run this program, and if they don't have a config file, they'll get an exception. And they may go and file a poorly documented bug report to the developer that says something along the lines, oh, the program crashed at startup. The developer, upon getting the bug report, will attempt to recreate the bug, and if they have a config file, the program's going to run fine. And this is going to start a feedback loop between the developer and the user, where the developer has to probe the user for more information to replicate the bug. This occurs because the developer is unaware of the computing environment that the user is using, and namely the fact that they're missing a config file. So record replay is a method that records the non-deterministic interactions your program has with the operating system. So this means the results of system calls and scheduling decisions, and generates a recording. This recording can be replayed, which will put the program in the same state by providing the same type of non-determinism to the program, and then the developer can easily replicate the bug. So this is a very useful tool for debugging. The problem is some of the known existing systems are rather slow. So RR is a state-of-the-art record replay system for Mozilla Firefox, and it can have up to 4x overhead. As a bit of a teaser, the system I'm going to talk about today, JMVX, can keep that much lower and stay underneath 2x. And we're going to achieve this by multi-threaded record replay that is also going to tolerate some benign divergences in the management of the JVM. So let's loop multi-version execution back into this before I explain how the system works. Something to notice is record replay is offline multi-version execution. So this is kind of the diagram of how a record replay system looks, where you will create a recording from your program, and later on you'll replay it. If instead of doing this at 2 different times and sending these recordings to disk, you sent this recording to a shared memory buffer and you split this between 2 JVMs, and you have maybe another process that's a coordinator that sets up these initial connections, what you're really looking at is not record replay, you're looking at multi-version execution. What multi-version execution buys you, if you have a follower that is a different variant, e.g. a newer version of the software you're using, as this software runs and potentially encounters errors, you may have a different variant survive the crash and you can provide continuous service. So record replay, very good for debugging. Multi-version execution, really good for providing continued service. And these 2 types of systems can be implemented with the same code base because their architectures are very similar. The problem is that both of these things are difficult for VM-based languages like Java. And this is because you have to deal with VM runtimes. So the garbage collector, the just-in-time compiler, and class loading, all of these mechanisms, particularly in Java, are designed to work differently every time you run the VM. And this problem would be, it would be much simpler to do these techniques over programs if only we were able to let the VM management bypass our record replay or MVX system and interact with the operating system. And this is the high-level design behind JMVX, where we're going to embed our record replay system inside of the bytecode. And this way, things that the JVM wants to do where it interacts with the operating system can go straight through, and we're going to focus specifically on library calls that the program makes, so things the Java developer cares about. In order for this to work, we need to understand what a non-deterministic API is. We need to know what we need to log. And we're going to be looking at methods in Java that will eventually lead to system calls. So we're going to use a little bit of bytecode instrumentation and dynamic tracing to help find these. So we're going to wrap native methods. A native method is a method you can call in Java, but the implementation is in C in the underlying JVM. So the first method is going to clear a global flag that's going to represent whether or not a system call has occurred. The method afterward is going to check if this flag is set, and if it is, log a stack trace for us to inspect so we can find the method we need to instrument. We need a mechanism to tell us if a system call occurs, and for that we're going to use strace, and we can configure strace to send the signal user2 back to the JVM, and we'll have a signal handler that, upon getting the signal, sets the flag. So using this method, we're able to identify a lot of methods that we need to provide support for, and this is how we identified all the methods in green across these 2 tables, and I'll go into how we do the bytecode instrumentation to handle these. So looking at the example for socket input stream.read, we're going to take the read method, we're going to rename it to jmvxread, and we're going to insert a new method with the same signature. And this is going to have some code in it, jmvx.r.get, which is going to divert into the jmvx runtime that handles the recording, replaying, or the leader/follower's execution. This .r.get is selecting the strategy. So for record replay, the recorder will call the underlying implementation to read data from a socket, log the fact that we read some data from the socket, and then return. Whereas the replayer strategy will read data from a log file, assert that this is the operation that should have occurred and that we haven't diverged, and also return. So that's how we handle all the methods that are in here in green. Let's focus in a little bit on the outliers. So I mentioned before that class loading is non-deterministic within the JVM. Every time you run it, the order classes are loaded and is going to change. So we needed to provide special support for class loading. Unfortunately, I don't have the time to go into all the details right now because I only have 15 minutes, so there's a lot more details in the paper. I want to focus a bit more on some of these methods here. All of these are required for multi-threaded program support, and this is a major reason why we're going to get speed up over RR. Everything in red was manually identified. We decided we needed to, or we realized we need to support these in order to get programs to run. The yellow block is a bit interesting because this is something that's automatically identified. To get concurrency decisions that are being made in programs, we need to look at synchronized blocks and synchronized methods. So before talking about how the bytecode for that is instrumented, I'll talk about how we enforce the concurrency decisions. So multi-threading, the ordering of events is handled by using a Lamport clock to provide a total ordering of monitor entry. And what this means is it's whenever an object is locked in Java. So here we have a diagram of a program that's running. It's got 2 threads. There are 4 events that occur that need to grab a lock. And every time one of these events occurs, it modifies a global clock and logs a copy of it. When we go to do a replay, we may see these events in a different order. In particular, event 3 is going to try and run before event 1, which is contradictory to what we saw during the recording. In this case, the logged clock that we see in thread 2's log is not going to agree with the program's global clock and is going to be delayed. And it gets delayed until eventually event 1 occurs on thread 1, and that updates the global clock to a point where event 3 can now sync and run. And this continues for the rest of the scheduling that I have on the slide. In order to provide support for this in the bytecode, what we do is we take a synchronized method and we desynchronize it. And then we're going to apply some similar tactics to what we did before, where we change the method name and we add a new method with the same signature. Some of the code that we have here is going to re-implement the synchronized logic where we're going to end up grabbing a lock, but only if the conditions for the vector clock are satisfied. Now, I mentioned before, we also provide support for multi-version execution, and a key reason why we can provide fast multi-version execution is because we use a ring buffer that is a fast shared memory queue. It's an off-heat byte buffer that we make using mmap, and it's managed with unsafe, which provides us direct memory access, which is something that you don't normally get in Java. The key point that we want to mention here is that there's no locks used in this design, so it's very fast. And I don't have a lot of time to go into this, so please check the paper if you're interested in how this is done. Something that we also need to deal with are divergences and handling them. So we have a little bit of program output here from PMD, which may be too small to read, so I'm going to highlight the fact that the divergence happens when we print how long it took the benchmark to run. We handle this in JMVX using a divergence handler. This is a method that you write in Java that you supply to JMVX that will get some details on when the event you expected is different or the data you expected is different. And you can write some code on how to handle that. So in this case, this is checking that we're at the end of a benchmark and then modifies what is printed at the end of the benchmark so we still get accurate timing data from our test harness. So with all that said, let's look at how JMVX actually performs. So I'm going to go into the cost of the bytecode instrumentation, how we perform for record replay, comparing with systems RR and Chronicler, the overhead for MVX, and how well JMVX scales, particularly by looking at what happens as we vary the number of threads and the size of the ring buffer. As a note, most of our benchmarks are from the Decapo benchmark suite. 11 out of 12 of them are, and the last benchmark is a server benchmark we picked up from another paper. A brief note, I'm going to mention 2 modes of JMVX, sync and no sync. Sync is when we're using all of the methods in this table. All of them are instrumented. No sync is when we're avoiding the things here in red and yellow, meaning that we don't have any support for ordering multi-threaded events. And the reason we're doing this is to have a fair comparison with Chronicler when we get there, because Chronicler isn't capable of multi-threaded replay. So to evaluate the instrumentation, we use a pass-through strategy. This means as soon as we get into JMVX, instead of worrying about doing any logging of events, we just go straight to the underlying implementation to measure the cost of diverting the execution. So for the no-sync instrumentation, we see a 2% overhead, and for the sync instrumentation, we see a 5% overhead. So we believe that's negligible. For record replay, we have good results when we compare against RR, namely JMVX has 1.25x overhead versus RR's 4.33x overhead, and 1.73x overhead for replay versus RR's 4.7x overhead. Something that we also like to point out here is RR fails for 3 of the benchmarks that we wanted to run, Aurora, JME, and Jython, and JMVX was able to successfully record and replay those. In terms of recording size, we're, for most benchmarks, on par with RR. There's a couple where we have about twice the size, particularly with H2 and loose search. When comparing with Chronicler, we deal with our no-sync mode because, as I mentioned before, Chronicler doesn't have multi-threaded replay. Something to point out, Chronicler was not tested on the H2 server or JME benchmarks. The data that we have on this slide actually comes from Chronicler's paper rather than us running the system because it's tied to a version of OS X that we don't have, so we weren't able to reproduce any results. And as I've mentioned a couple times, Chronicler doesn't provide replay data. Something I do want to point out from this slide, well, I guess first I should go over, JMVX does beat Chronicler in recording overhead with 1.08x overhead versus 1.14x. But another thing that this helps us stress is you really need multi-threaded replay. You can't get away with just recording the results of some of the system calls or the library calls that those are coming from because you'll just end up diverging due to scheduling decisions that happen on a lot of these multi-threaded benchmarks. And that's why in our replay, we aren't able to replay things like FOP or H2 without the multi-threading support anyway. For MVX, we see our leader has a 1.7 or 1.47x overhead, and the follower has a 1.8x overhead. And I think I should now go into talking about the thing I'm assuming everyone's eyes shot to, and that is why do we perform so poorly for loose search? And this is because our vector clock is biased towards the leader, and loose search is a benchmark with many short critical sections. And every time we have an event that attempts to run out of order, we have to delay a thread. So everything in red in the figure that I've brought back from the Lamport clock section is slow. And these delays really add up and give us poor performance on loose search. Another test we did was we varied the size of the ring buffer for all of our benchmarks, going from 1 megabyte, 10, 100, 250, and 500 megabytes. Loose search, again, points out another interesting part of our development here is that if you have an improperly sized circular buffer, particularly if it's too small and the follower isn't processing events fast enough, it can actually back up the leader. And this is very important because the leader's delay is what the user experiences. The follower can lag behind, but it shouldn't lag behind too far. Finally, we did an evaluation on how does our recording speed and replay speed change as we vary the number of threads. And what this pointed out to us is that we have very poor performance for single-threaded benchmarks. Particularly H2 when run with one thread, and Jython, which is a Python interpreter in Java. When running one thread, the JVM gets to use optimized locks that vastly outperform our vector clock. So to conclude, JMVX operates in the bytecode rather than directly on system calls, which allows us to tolerate benign divergences in the VM's runtime and focus particularly on the calls that are important to a Java developer. We're capable of supporting both record replay and multi-version execution. We use dynamic tracing in order to identify the methods we need to instrument to support a program. And we outperform R, the most popular user space record and replay tool. So the code is available on GitHub, and I encourage you to check it out if you're interested. And with that, thank you for your time.
All right, thank you. Great talk. Any questions? Yes. Yep, I think so.
Hey, thanks for the talk. You mentioned that multi-threaded replay is very important.
Yes.
So I was curious, can you guarantee that multi-threaded record and replay is both sound and deterministic, even in the presence of things like object.wait, notify all signals and conditions and things like that, where the JVM sort of can arbitrarily pick one thread to resume from a waited state and reclaim some monitors, etc.
So we were able to implement wait find. That was one of the ones that we manually said we have to go in and add some support for, and it's through this vector clock implementation we were talking about. There are cases where JMVX will not give you guarantees, particularly with signals. We don't do any replay over signals right now.
All right, thanks.
Hi, thanks for the talk. I was curious about your comparison to RR in particular. I guess I recall their work reporting that the overhead was maybe like less than 2x, where you're sort of seeing 4x or more. So I was just wondering if that's kind of down to just choosing different benchmarks or something else.
So the main thing with RR's extra performance is that it takes a multi-threaded program and it runs it on a single core at any given time.
Yep.
Right, so it's really, I think, just based on the fact we can run multiple threads, and a lot of these benchmarks are multi-threaded.
Yep. Okay, thanks.
Yep.
Hi, thanks for the talk. So I was wondering, like, how do you take care about the garbage collector that might be running in parallel in the JVM?
We allow it to diverge.
Okay.
So one of the things we wanted to get to is we're focusing on trying to record and replay specifically what's happening with the Java application, and seeing that the idea behind the garbage collector is to run on its own in every time you run the VM. We just let it do its job. There are cases where this can cause complications in replay, specifically if you're using weak references for memory-sensitive caches.
Yes.
In that case, we can have replays that diverge as well. So I should have mentioned that with the first question.
Okay.
So,
yeah, thank you.
Good question.
You said that there was like a less than 10% overhead, like if you like just doing the, call a different function and then call back to the function that you actually wanted to call. Is that, this might be a naive question, but is that like just measuring the additional overhead of like doing that function call?
Yeah, we're just dealing with what it takes to do this extra method call moving in the bytecode.
How do you know that it's not like inlined?
It could be because the JIT's technically running below us, and in fact, that's kind of a benefit for us.
Fair enough.
Any other question? Right, I have one question since we have some time.
Yes.
From a replay perspective, it's really cool that you can replay the schedule of threads. From a bug finding perspective, it's a little unfortunate, right? Because some bugs that I might be looking for might have to do with different schedules.
Yes.
Is there any hope from a bug finding perspective of doing something different with threads?
Ooh,
like
we've had some discussions on it, particularly if you can post-process a replay and find out different ways of doing the scheduling, like if you can rewrite the vector clock between when you do a recording and when you actually do replay to see what would happen with different schedulings. That's work that we're still thinking about doing. We haven't made much progress with it yet, but there is hope.
Okay, cool. All right, well, let's thank David one more time. Thanks.
Thank you.
I'll give it a moment for the microphone. All set? All right, for our next talk, it'll be about liblisa, and Jos is giving the talk.
Thank you. So, when we have a program that's been compiled to a binary, all that we have is a bunch of bytes. And we might still want to know what these bytes do, what the program does. And if we don't have the source code, maybe because this is legacy software, or maybe because this is malware and we simply don't have access to the source code, then we have to analyze these bytes. And so this is still a very vague question, what do these bytes do? So to make that a little more specific, from my point of view, a CPU is a machine that repeatedly updates CPU state. And it does this by fetching an instruction, which is just a sequence of bytes, and then according to this instruction, it performs some kind of modification to the CPU state. And so the more precise question to ask is, how do these bytes actually modify the CPU state when we execute them? And so that's essentially what CPU instruction semantics are. They take bytes or instruction as input, and they produce some kind of description of how the CPU state is updated as output. And of course, ideally, we would like that to be in a format like this, which is nice and formal and machine readable. But that's not what we get in practice on x86 CPUs. What we get is a 5,000-page PDF with natural language descriptions of each and every instruction. So if I want to write an analysis tool that analyzes binary, I need to manually translate all of these 5,000 pages to something that my analysis tool can use. And to make matters even worse, when I have done that, as it turns out, these manuals are actually not that accurate. Basically, every time someone takes a look at them, they find inconsistencies, errors, and discrepancies. So now I have spent a lot of time writing down these semantics, and now they're not even correct. So when I first ran into this issue, my thought was, well, we should automate this. We should take the human out of the loop and do this all automatically. And that is essentially what liblisa is. It's a tool that takes CPU as input and automatically analyzes it and produces CPU semantics as output. And it only needs two things for that. It needs a description of what the CPU state is, so which registers are there, which flags, etc. And it needs a way to observe execution of an instruction. So it needs to, given a certain CPU state and an instruction, needs to be able to check what the modified CPU state is after executing that instruction. And from that, it can automatically infer the semantics of all instructions on the CPU. And so how do we do this? Well, a straightforward approach might be to simply start enumerating every possible bit string. And then we can check with the CPU observer if that bit string is actually a valid instruction. If it is, we yield it, and that gives us a list of all instructions on the CPU. And then we just need to infer semantics for every instruction. And this might work for a smaller CPU architecture like RISC-V or maybe ARM, where the amount of bit strings that you might need to enumerate is limited. But this doesn't work for x86, for the simple reason that on x86 you have instructions like this. And this is only 40 bits. You can easily have an 80-bit instruction or even longer. We're not going to be able to enumerate 80 bits of instructions. So we need to find a different way to actually enumerate all instructions on the CPU. And one of the ways to do that is to realize that this instruction is actually not that unique. There aren't billions of different instructions on the CPU that all do unique things. For example, this instruction, the last 32 bits are actually just an operand, an immediate value that is used to update the CPU state. And the 3 bits before that are just a register operand that is used to write the result of the computation that this instruction does. So what we can then do is we can start inferring the way these operands are encoded into the instruction. And we can replace this immediate value with a part that says, well, here is a 32-bit immediate value. And this operand, well, it can be a part that indicates that here is the destination operand of this instruction. And now we have an encoding that describes 32 billion different instructions that only differ by operands. And that is what is going to allow us to actually enumerate all instructions on the CPU. Because what we can do is we can, when we've done our enumeration and we have a bit string, we can immediately start analyzing the encoding of this bit string. And that gives us a group of many instructions that all only differ by operands. And we can then use this encoding to speed up enumeration. So we can skip all of these 32 billion instructions that do the same thing modulo its operands. And that makes it feasible to actually enumerate large instruction spaces like x86. And then all that's left after that is to run some standard program synthesis to synthesize the semantics for each instruction that we found. And so that is how liblisa works. Now, of course, if we run this on an actual CPU, we might get different results on different CPUs. And in fact, it's very likely that we get these because x86 has some undefined behavior in its instructions. And what that really means is that these instructions are doing something that's implementation defined. So every CPU implementation can pick its own way of executing this instruction. And that means it's actually very likely that we'll find differences among different CPUs. And so that's the reason why we've actually analyzed 5 different CPUs. So we've run LibLisa on 5 different CPUs, on 2 AMD CPUs and 3 Intel CPUs. And it takes roughly 7 to 21 weeks to run this analysis. And that gives us 120,000 different encodings, so 120,000 different groups of instructions that only differ by operands. And one of the interesting things is that we found a bunch of undocumented encodings on AMD CPUs. And so these instructions are essentially copies of the vperm-q instruction. And they exist because these instructions need a very specific bit in the instruction bit string to be set for them to be valid instructions. And AMD forgot to check whether this bit was set or not. So all the instructions where this bit isn't set also turned out to be the vperm-q instructions on these CPUs, while they shouldn't be. And finally, we are also able to, as it turns out, synthesize this undefined behavior that some instructions have quite well. So for around 90% of all encodings that have undefined behavior, we're able to synthesize their semantics. So that means that we can also compare these differences. And when we do that, we get a table that looks something like this. So here at the top are again the 5 architectures that we analyzed, and then each group is a group of instructions that has the same kind of differences between its implementations. So for example, group 0 is the group where all implementations do exactly the same thing. So these instructions are all equivalent. But group 1 is a group where there are actually 3 different CPU implementations. So architecture 0 and 1 share an implementation, architecture 2 and 4 share an implementation, and architecture 3 has another implementation of these instructions. And when a symbol is missing in one of the rows, that simply means that this instruction is not supported on the CPU. That can be, for example, when you have CPU instruction set extensions like the SHA-256 instructions that are not actually supported on all CPUs that we analyzed. And one of the interesting things that we can do with this table is that we can use it to identify instructions that we can use to fingerprint the CPU that we're running on. So for example, if we take one instruction from group 1 and one instruction from group 7, and we observe how they behave, what their implementation is, that's enough to actually identify which of the 5 CPUs we are running on. For example, if we check the instruction from group 1 and its implementation turns out to be the red circle implementation, and we check the instruction from group 7 and it's a blue square implementation, well then we must be running on architecture 2, because that's the only architecture that has this specific combination of implementations. So now we have, of course, a lot of semantics, and we might also want to make sure that they are actually correct. So to do that, we picked the formal semantics by Dasgupta et al., who manually implemented most of the instruction set reference manual, most of these 5,000 pages of PDF. They implemented manually in a model, and we are going to compare their semantics against our semantics to see if there are any differences. And when we do that, we did find some differences. So we found 32 variants where there was some kind of difference between the semantics from Dasgupta and the automatically generated semantics from LibLisa. And we manually looked at all of these semantics, and we classified whether they were an error in the manually written semantics or an error in LibLisa semantics. And it turned out that most of the cases, in 28 of these cases, was actually an error in the manually written semantics. But there were also a few cases where LibLisa's semantics were incorrect. And that's caused by the synthesis that we used. So the program synthesis that we use forms a hypothesis and then tries to verify this hypothesis by fuzzing. And if it has encountered 2 million cases where this hypothesis seems correct, it will consider the entire hypothesis correct. And as it turns out, 2 million cases is not quite enough to always capture the full behavior of some of these instructions, which is why there were some errors. And this can, of course, then be fixed by either increasing the threshold on the number of cases that you want to observe before you consider your hypothesis valid, or you could fix this by finding your test cases smarter and increasing the quality of the information that you get from each counterexample that you find. So finally, if you're interested in taking a look at these semantics, I would recommend using explore.liblisa.nl. This is a website where you can look at these semantics in a sort of human-friendly way. And you can actually also simulate the execution of these instructions and export it to SMT code if you want to. So in summary, LibLisa is a tool that automatically discovers and infers instruction semantics. We analyzed 5 different architectures and found differences in the undefined behavior. And all of these semantics and source code is all available under open source licenses. Thank you for your attention. If there are any questions, I'd be happy to try and answer them.
Go ahead.
Hey, nice talk. Can you hear me?
Yes.
Yep, cool. I guess you can infer you infer the semantics from architectural state, is that right? Can you infer stuff that you wouldn't necessarily observe directly? I'm thinking like microarchitectural things or side channel-like things that require maybe another thread to do some magic to...
So it's not, in this work, we're only looking at the actual architectural state, so we're not doing any of that. But I am aware of some tools that automatically, for example, try to infer the timing of instructions. And that could also be combined with this. So, it depends on what exactly you want to observe. But as long as it's observable, you can do it.
Yeah, I mean, I'm just thinking from a CPU design perspective, a lot of the value is in how they make it fast under the hood. And it might be useful to have the semantics for that as well as the visible stuff. But that's cool, thank you.
Hi, really cool work. Sometimes CPUs ship with bugs, which is okay because you just get your computer to patch the microcode really early on and you're fine. Could you use LibLisa with microcode patched or not patched to see, kind of to reverse engineer the bug if the manufacturer doesn't really reveal what it was?
So there are some cases where you can do this, yes. So I believe the Reptar bug was one that, unfortunately, it was out of scope, the specific instructions that caused it. But if it had been in scope, we would have likely found that bug as well.
Okay, cool. I have one more question. What about hardware transactional memory instructions? Those take a lot of state that lives, in the cache and all of that. So can you work with those?
It's out of scope in this work.
Okay.
I'm not familiar enough with the exact details to be able to tell you if it's possible to analyze those instructions or not.
Okay, I encourage you to take a look. It's super cool.
Thank you.
Thank you.
Did you find any NSA backdoor?
Any what, sorry?
Any NSA backdoor?
No, I did not. Unfortunately not.
The correct answer is neither confirm nor deny.
So I would imagine that if you have some arbitrarily niche or complicated instruction, I don't know, just say we have an instruction that does a matrix multiply, then now your tool that can generate hypotheses about the semantics of that needs to be able to model arbitrarily complex instructions. Like, how does that look? I mean, if I came up with something like a cryptographic instruction that's doing some crazy hash function, are you able to model that? And that seems like a very hard problem in of itself. So can you speak more about that part?
Yes, so yes, in general, it's just a hard problem. But one of the advantages is, so it's hard with program synthesis in general. But one of the advantages with doing it with CPUs is that a lot of these CPU instructions are very simple, right? I believe something like 70% of all encodings that we found are just doing data moves.
Yeah.
So yes, there are some instructions, for example, cryptographic instructions that are hard to synthesize. And in such a case, you might have to add a specific operation that does the operation you want to synthesize to your synthesizer.
Okay, thanks.
Any other audience question? So I have one more. If I understand, so you're inferring these templates, the shapes of the instructions, and I'm wondering how important is it to infer that as opposed to have that one of the things a human provides? Because usually you can see the beginning of the reference manual will say, we use these patterns for instructions.
That's a very good question. So my point would be that, yes, we might see it in the reference manual, but how do we know it's actually implemented that way in the actual CPU? And especially for example, undocumented instructions, how do we know how they are encoded? So I think it's valuable to spend some CPU time on automatically inferring these if it's possible.
Did you compare the inferred templates to the ones in the manual to see whether there were differences? Okay, I would be interested, but that sounds like actual work too, right? Okay, let's thank Yost one more time. Thanks. We're going to take it slow on this transition to stay synchronized with everyone. So we'll do that. Meanwhile, is our fourth speaker here? Okay, I'll just sync with you. Thanks. All right, thanks for holding on, everyone. We're going to wait 30 more seconds, and then we'll be synchronized with all the other sessions, and that will be perfect. Synchronization is important, yes. We have a model for synchronization here. All right, as you know, because you've had lots of time to read the great title slide here, we're going to be hearing about extending the C and C++ memory model with inline assembly, and of course, Paolo is giving the talk.
Yeah, thank you very much for the introduction. So this is joint work with Aurélie Lahav, Victor Vafayatis, and Azelia Haad. So I would like to start with a brief overview of the talk by explaining what's the problem we try to solve, what's the motivation for tackling this problem, and what are the challenges. So simply put, the problem is to devise semantics of concurrent programs with inline assembly. And the motivation is that inline assembly is a very powerful tool of C++, but unfortunately it is under-specified. So for those who don't know, inline assembly allows one to insert snippets of x86 assembly directly into C++ code. And there are many applications, many reasons why one would like to do so. One of them is to write efficient code directly in assembly. A second one is to have access to instructions that are not in C++. And a third application is to customize the call convention of naked functions. So to give a concrete example of this second application, I have here a program that uses inline assembly to have access to non-temporal stores. So a non-temporal store, simply in simple words, is a store that bypasses the cache. We are going to revisit this instruction on the talk. And we are going also to use inline assembly blocks under a much simpler syntax. So I'm going to refrain myself from explaining the details of this block. All that we need to know to understand this example is that this non-temporal store is going to move the value 42 to the variable destination. So by the end of the execution of this inline assembly block, the variable destination will store the value 42. So the challenge of devising semantics for concurrent programs with inline assembly is that the architecture, x86, and the source language have incompatible concurrency models. So in the first part of the talk, I'm going to elaborate more on what are these incompatibilities. And in the second part of the talk, I'm going to explain our extended concurrency model for C++ with inline assembly. To appreciate these incompatibilities, it's good to have a basic understanding of the concurrency models of C++ and x86. So I prepared this short slide where I introduce RC11, the model for C++, and EX86, the model for x86 assembly. So in C++, to access memory, we have to specify a mode, an access mode. And there are basically two classes of access modes. There are atomic access modes and non-atomic access mode. So atomic access modes are used to establish synchronization, whereas a non-atomic mode can only be used once you establish synchronization. And I'm going to use this example to explain access modes. And it's good to understand this example because we are going to revisit this example very often throughout the whole talk. And we have here two threads, one that performs two writes to the variable x and to the variable y, and another thread that performs two reads in the inverse order. And here we can think of y as a flag that tells whether the variable x has been updated. So if the thread T1 reads 1 from y, we would expect that it reads 1 from x. So this is the case if we used the SC mode, which is the strongest one in terms of synchronization guarantees. But it is not the case if we use the weakest mode in terms of synchronization guarantees. And what is key in C++ is that we have a mode in between, relax and SC, that allows you to restore synchronization. Now moving to x86, to the model of x86 assembly, there are basically two properties that are important for this talk. One that by default x86 disallows this weak behavior where we read 1 and 0. And A second property is that using non-temporal stores, the weak behavior is allowed. And the reason is that a non-temporal store, again, is a store that bypasses the cache. So it could be the case that X goes to T0's local buffer, and Y goes directly to memory. So T1 would read the value 1 from Y in memory, but would not read the update to X. So having understand this, we can already appreciate the first incompatibility between the C++ memory model and x86 memory model. And we can see that a non-temporal store breaks release acquire synchronization. So a release write in when the target of compilation is x86 is compiled to a plain write. So as we saw before, a non-temporal store can be reordered with a plain write. So in this case, it could be the case that X and Y are reordered, and we would see the weak behavior. So the challenge is to relax the model of C++ in such a way that this behavior is allowed. And we also want to suggest new ways to restore synchronization in the presence of non-temporal stores. A second incompatibility is due to compiler optimizations. So here we have basically the same example as before, but instead of a non-temporal write, we have just a plain store. And the compilation to of this program is to plain access modes in x86. And as we saw, this behavior is disallowed. So this could suggest that we wish to enforce the same constraints, the same consistency constraints of x86 to the source code, but that would be unsound because of compiler optimizations. So RC11 allows the mode, the relaxed mode to be, relaxed reads to be reordered. So if the compiler performs this optimization, then we could witness the weak behavior. So the challenge here is that x86 consistency breaks some of the compiler optimizations. A third challenge is that we cannot model inline assembly access using the standard, the existing RC11 access modes. So we cannot use SC because it's stronger than inline assembly access, because the compilation inserts strong memory fences. And we cannot use the other mode of access because they are weaker than inline assembly, which is not optimized like the other ones. So the challenge here is to devise new modes to describe inline assembly accesses and discover how they relate to the existing ones in RC11. So now moving to the presentation of our solution, our extended model, I'm going to explain how we solve each one of these challenges. So the idea to solve the challenge of non-temporal stores breaking release acquire synchronization is not to remove these synchronization edges between release and acquire access, but actually to remove the synchronization access within a thread. So in RC11, every local access is by default synchronized. But now in our extended model, we remove these synchronization edges when it's a non-temporal store. However, we do allow the synchronization edges between non-temporal stores and store fences, which is an instruction from x86 that's meant precisely to stop the reordering of non-temporal stores. And by transitivity, we would get the synchronization between the write to X and the read to Y. So the second idea to solve the problem with compiler optimizations is to enforce x86 consistency only on threads that include inline assembly blocks. So that's actually a great simplification of how we actually formalize this idea, but is a first simplification to understand. So here, this weak behavior would be disallowed, but the because of compiler optimizations, x86 would not apply to consistency, would not apply to this thread, which could witness the weak behavior. And third, to tackle the problem of access modes not handling inline assembly access, we introduce 3 new access modes: TSO for plain read and writes, a mode for non-temporal stores, and a mode for store fences. So what's striking about this ordering is that we don't have a total order anymore on the guarantees of synchronization. And we also, it's weird that we don't have any relation between non-atomic access and non-temporal stores. And it's also a bit striking that we don't have TSO as weaker than SC. So to explain why we don't have these orderings, I'm going to show examples where we have each one of these modes weaker than the other. So here's an example where non-temporal stores can be weaker than non-atomic access. And the example is basically just the same as before, because non-temporal stores break the release-acquire synchronization, whereas non-atomic access don't. And also the converse is true. Non-atomic access can be weaker than non-temporal stores because racy non-atomic access leads to undefined behavior, whereas in our model, racy access to non-temporal stores do not lead to undefined behavior. So this begs the question why we made this choice. And there are many reasons, and here we cite only 2. One is that one of our design goals is to have programs fully written in inline assembly have x86 semantics. But if we made racy access to inline assembly UB, then we would not be able to have this property. And a second reason is just that inline assembly is not optimized as non-atomic access. So we don't need to introduce UB to justify some of the soundness of these optimizations, like in non-atomic access. So finally, why TSO is not weaker than SC? So here's an example where SC is weaker than TSO. And the reason is that in RC11, SC access, when you mix different modes of access to the same variable, then it might be the case that the semantics is weaker than SC. So this is an example where we have this weak behavior allowed, even though we use SC. We do not have the weak behavior on the thread that use inline assembly, because as I explained, threads that use inline assembly abide by x86. We also have some properties of this model. So we have the property that programs fully written in C++ have unchanged semantics with respect to RC11. We also have the property that programs fully written in inline assembly have x86 semantics. And we have a data race freedom theorem, which means that programs with data races only on SC axis have SC semantics. Finally, we proved the correctness of compilation and of many compiler optimizations, with the notable exception of one compiler optimization called sequentialization. Sequentialization merges 2 threads into one by interleaving their instructions. And the reason why this is not sound in our model is because it is not sound in x86. And the reason why it's not sound in x86 is that there's a difference in x86 between reads, internal reads and external reads. External reads enforce synchronization, whereas internal reads don't. So if you sequentialize, you turn an external read into internal read, and you lose synchronization. So to conclude, I justified why inline assembly is an important tool, and I explained that in this talk we wish to provide semantics for concurrent programs with inline assembly. I explained some of the challenges in coming up with such a model. One is that non-temporal stores break release-acquire synchronization. A second one is that x86 is compatible with many of the compiler optimizations. And a third reason is that inline assembly access cannot be modeled via RC11 existing access modes. I explain how our extended model tackles these challenges. So in particular, I explain how to restore release acquired synchronization using star fences. The idea that x86 consistency only is limited to the scope of threads with inline assembly. And I explain the new access modes to model inline assembly access. And I also explained some of the properties of our model, namely that it extends RC11 and x86. It satisfies a data race freedom property, and it proves many of the compilation schemes correct and compiler optimization as well. Thank you very much. I'll be glad to take questions.
Questions, go ahead.
Hey, nice work. I'm glad someone's done this. It's been a long time coming. A couple of questions. I'll ask you one offline because it's probably a longer one. First two, compilers, obviously they support all of the architectures that they generate, right? So you can have inline assembly for ARM,
Yes.
IBM, MIPS, x86, RISC-V, so on. Have you thought of like automating this so you can come up with a family of models for each architecture the compiler will target? Because super handy to be able to reason about all of these different architectures. But also, how would this sort of manual approach of mushing these models together deal with changing architecture models? Because they have changed over the years, right? That's two questions.
Yeah, so unfortunately, our solution is tailored to x86, and it gives some ideas of how to come up with a general way of combining models, but as it stands now, it's tailored for x86, and I have ideas of how to extend this work to ARM, but due to many incompatibilities between these two architectures, it's difficult to think about a general way of combining them.
Yeah, I mean, that's my third question. So RC11 forbids load buffering, but you can observe it on ARM, so that's kind of an incompatible set of arrows,
yes,
right? So
exactly.
we can talk about that later, but nice work. Thank you.
Thank you very much.
Thank you very much for the talk. So my question is, suppose you have a atomic read in one thread and inline assembly read in another thread, and these two operations are not sequenced. Is that allowed under this model?
What is allowed?
So like two racing reads, one atomic, one from inline assembly. Is that like something that your model permits?
Yes, yes.
Okay, because I had a debate on the C++ mailing list about this because they said that you cannot, they believe in typed memory basically. You cannot have an atomic operation and a non-atomic operation on the same like memory location. Which obviously you can do that through inline assembly.
Yes, yes. I mean, on our toy formalism, that is perfectly fine. In actual C++ code, you would have to do some casting to change the type from atomic to just the type of a variable, an integer variable. But our model handles gives semantics to programs that mix these accesses.
Okay, thank you.
Hi, cool talk. Does your model support operations that work on more than just an integer? So these streaming operations are used to move data fast, and like if your CPU has a VX, it's going to try to move like 512 bytes at a time.
Yeah, thank you for a question. No, it doesn't support. Our model is limited to integers.
Okay.
Yeah.
Okay.
I mean, the generalization to other basic types is straightforward, but to more complicated instructions, as you mentioned, it's not straightforward.
glibc uses that a lot to move data fast. So I wonder if you could find like miscompilations where the program doesn't match what the developer wanted, if you call like memcopy or something like that. I know they're not atomic, but different threads might try to do it, so no.
Yeah, that's definitely an interesting idea for future work. Thank you very much.
Thank you.
Okay, we're right at time, so let's thank Paulo again. Thank you.
Thank you.
right, next up we're going to hear about TorchQL, and Aditya is giving the talk.
Thank you. Yeah, hi everyone, I'm Aditya. I'll be talking about TorchQL, which is a programming framework for integrating constraints in machine learning. So as we all know, machine learning models make a ton of mistakes, and they can range from things that are a bit more critical, like in this case where a person is not being detected by an autonomous vehicle, to things a bit more benign like bias in GPT 3.5, few mislabeled training data, and imputation errors in medical data. And in every case, finding those errors, those specific errors that we are looking for, is kind of tricky. To do so scalably, people typically go to performance metrics like accuracy, or use statistical techniques like outlier analysis or error rate analysis. But a problem with all these techniques is that they aggregate errors and don't really give you fine-grained feedback. So if you want a really specific error, you have to filter through a lot of potential errors to actually get the specific kinds of errors that you want. So case in point, I don't know if this is really visible, but over there you see 3 frames in a video, and there is a person in all 3 frames, except the person is detected in the first 2 frames by an object detection model and is not detected in the last frame. These predictions are given by a model called OneFormer, which has a pretty high accuracy on the Cityscapes dataset, which is for autonomous driving. And even then, it's unable to actually predict the person in the third case. And this is a very critical error, but it's also a very sparse error because it only occurs around 627 times out of 15,000 frames. So imagine filtering through all those frames just to find these kinds of errors. So we then looked back at this and we realized that this is a pretty basic property of object permanence that is being violated by this model. And we kind of extrapolate that to arrive at the core insight of our paper, which is erroneous model predictions can be cast as violations of integrity constraints. So we can specify integrity constraints over the outputs of models, and looking at their violations can give us specific kinds of errors that we want to get. So now that we have that, let's see how we can specify integrity constraints. So we will need a framework in order to perform this specification. And that framework needs to support a variety of features. So for instance, the framework needs to have a flexible schema because we are dealing with Python, and Python has objects of various kinds, not just numbers and strings that most database frameworks are used to. We need to support user-defined functions because constraints like object permanence are quite complicated to define. So you need to allow for the specification of those kinds of constraints. And you need to have querying abstractions because you want people to focus on actually specifying the constraints rather than writing how those constraints will be evaluated over the model. And that's what querying abstractions helps with. And then we looked at a few different frameworks. So we looked at Pandas, MongoDB, and Python. And in pretty much every one of these cases, there is some issue. So Pandas does not have a flexible schema. It only supports numbers and strings. MongoDB does not let you define user-defined functions. And Python, you need to basically implement the entire thing in Python from scratch. And so we proposed TorchQL, which is a querying framework that is integrated into PyTorch that lets you write queries as modules within your machine learning pipeline that you can just plug in and evaluate models over. So the setup is kind of like this. You have a user who can instantiate a TorchQL database and supply data to that database. This data can have objects of any kind. Over here, it's images. And in code, it looks something like this. You instantiate a variable called db, which is a TorchQL database, and you register the data set in that database. The data set string is denoting the name of that particular table, and it can be used for defining subsequent queries. Then the user writes TorchQL queries that are given to the database. Over here, our TorchQL query is going to try to get the predictions of the models. So we are looking again at the one-former model. And once we instantiate the model, we can start defining the query. The query is defined as having a name called preds, and it is based off the dataset table. And what we do then is we use a projection operator that operates over every single row of the dataset table and applies a function on every single row. Over here, our function is the model itself. We supply b equals 128 as a way of saying that we want a batch size of 128, so we have batched evaluations. It helps with scalability. And then once we have this query, we can run the query and give the results back to the user and also store them back in the TorchQL database for the user to write more queries on. And that looks something like this. Now that we have these predictions, let's look at how we specify object permanence. So I'm going to take you through my thought process on how I started specifying object permanence using TorchQL. And I started off with the simplest query possible. I looked at all the frames where at least one pedestrian is predicted, just as a starting off point. So in TorchQL, that looks something like this. We have a query named people count, which is based on the predictions. And we simply apply a filter operation over that, where you count the number of people in every single frame, in every single prediction. Now, count people, as you can see, is a function that has been defined somewhere else. And it can be arbitrarily complex, but for this case, it's literally a few lines of code that just takes all the people predicted and counts the number which are actually people. On the right, you can see the Python version of this query, and you can already see that it has some added infrastructure that makes it a bit more complicated. It's not a big deal right here, because the query itself is kind of simple. But as we go to more complex queries, we'll actually see the difference. Now, this is a very simple query, and it gives us a lot of false positives. So we move on to a slightly more complex query, which is finding all the cases where the number of people predicted changes from frame 1 to frame 2, where these two frames are consecutive. So what we do is we again look at the base prediction table, and we perform a self-join. But we perform a self-join over the condition that the predictions from the second column will be of a frame after the predictions from the first column with a time interval of 1 second. So that is FID plus 1 and FID. And then we extend the filter operation from the previous query to now filter for a difference in the number of people as opposed to just filter for the absence of people. The Python version, again, requires a bit more infrastructure in order to implement this. And over here, you need to start nesting for loops and adding more if conditions to actually express that. And then finally, we arrive at the actual object permanence query. Now, this is obviously a bit more complicated, but you can see in the first 3 lines of the TorchQL code, here's a 3-way join, because we're looking at 3 consecutive frames. And we then perform a few projections to track objects across those 3 frames, and then we perform a filter that removes the cases where there's no prediction in the last frame. And now here you can see the difference between the TorchQL code and the Python code. The Python code is way more complex to actually write and even read for anyone else coming in and trying to see what this integrity constraint is. And so we see that TorchQL provides these primitives that makes it easy, and in total we have 8 primitives or operations that lets us write. In the process of making TorchQL, we wrote hundreds of queries, so these 8 encompass a pretty good set of primitives. Another example is, so using these primitives, we were also able to extend the functionality of TorchQL to actually apply to constraint generation. So what we do over here is we see that there are several times when LLMs will generate outputs that are incorrect or that are easily, like, I asked for a number, but I got some text instead, and I don't want that. And this is basically constraint generation for LLMs. On the left, we've written the TorchQL query that achieves constraint generation. But I'll explain the diagram on the right. So on the right, you can see that there is a function called genk that is responsible for generating the outputs of an LLM. What this does, it takes a chain of thought prompt, it takes a data set, it takes an LLM, and it produces answers for every single entry in the data set. Then it gets passed on to a constraint. As you see over here, the constraint is a lambda function. So this constraint can be literally anything. So you can even imagine a code generation LLM being constrained by the constraint that the output needs to be syntactically correct or adhere to certain static checks or things like that. And then it looks at the constraint and then it outputs the answer which actually obeys the constraint. And we compare this chain of thought to our standard chain of thought on the top and to LMQL chain of thought, which is another constraint generation technique, but that works token by token. And we see that TorchQL chain of thought is faster than LMQL chain of thought because we are able to scale much better. And it's also more accurate and produces more valid results than LMQL chain of thought. But it's still slower than your traditional chain of thought prompting because we have the added overhead of providing the constraints. And so we look at other uses of integrity constraints as well, and they include label correction, outlier detection, bias discovery, and in general, we implement all of these queries, but for evaluation, we consider 11 of those over 5 different tasks. And here are some numbers as to like the number of operators in every single query, but it's kind of a lot of detail. But essentially what we do is we write the same query in every single framework that you see on the top over there. So we write the same query in pandas wherever it is possible, in ArangoDB, which is an in-memory version of MongoDB, in NumPy, that is only possible for 3 of these queries, and in Python. In every single case, we write it in a way we expect reasonable programmers to write in that particular language. And specifically in Python, we optimize the Python code as, to the level that TorchQL is optimized. And this is important. So we see over here that TorchQL always runs slightly slower than Python and NumPy, which makes sense because TorchQL is a Pythonic framework. And the overhead that is provided by the abstractions is negligible, But TorchQL runs much faster than ArangoDB and Pandas that are actual query processing frameworks. Now, the reason this is, the optimizations in Python were important was because in the cases of joins specifically, unless you optimize the Python code, your Python code runs much slower than TorchQL. So SQ1 took around 10 minutes and actually timed out over here if we did not optimize the Python code. But we brought, but to make things fair, we optimized it and brought that down to around 43 seconds over here. We also look at conciseness, which is just a way to approximate how much easier TorchQL queries are to write. For that, we just look at the number of tokens we needed to write the queries in every single system, and usually TorchQL requires the least amount of tokens to write them. We also conduct a user study where we give the users 3 tasks. Task 1 is like the simplest task and was basically achieved by the users in around an average of 4 minutes. And task 3 was the most complex one, which was difficult even for me, even though I wrote the system. But users were able to achieve this in around 50 minutes with a good performance, in general. All these users were mostly graduate students with 3 or 4 engineers as well, who were well versed with machine learning in general, but they had never seen TorchQL before, and they had to essentially learn it from scratch when they were giving this user study. So given all of that, we come to what we plan to do in the future with TorchQL. So as you saw over here, TorchQL is more of an evaluation framework where you get the predictions of a machine learning model and then you evaluate them or you constrain them. But we want to really get TorchQL into the training pipeline by essentially figuring out a way to effectively express differential versions of these integrity constraints and allow us to train models constrained by these integrity constraints. That's half of the battle is already done because TorchQL allows for end-to-end differential queries, but we still need to work on this. We also want to look at database optimizations in TorchQL and how we would be able to end-to-end synthesize TorchQL queries so we can hopefully give a NL natural language prompt and get the queries back. And so in conclusion, we're proposing a framework for programming and checking integrity constraints. And we showed that TorchQL is expressive, scalable, and interactive. And the code for TorchQL is available on our GitHub in case you want to try it out and give us feedback. And yeah, thanks for listening to the talk. I can address any questions now.
Go ahead.
Hey, Will from Brown. I'm curious about the performance comparison with pandas. My understanding is pandas is slower due to something about an inflexible schema, but can you elaborate on that? Like, what is TorchQL doing that permits it to be faster than pandas while having a comparable API?
So, okay, so pandas is not slower because of an inflexible schema. It's just that we cannot express certain queries in pandas because of the inflexible schema. So over here, we were able to express every single query in pandas. The reason pandas is slower mostly comes from the joins that are required by these queries. So SQ1 and SQ2 are both join-heavy queries over here. So as we can see over here, they require joins over really large data sets. So it's so this is object detection. So this is the 15,000 frames that we saw in the example in the beginning. That's where pandas mainly suffers. It's in the join process when you have joins over a user-defined function. So for pandas, you have to actually create new columns that run the function, get the outputs in those new columns, then join based on those columns. And that's where you get all the added overload. Added overhead.
Whereas how does TorchQL avoid doing that?
So TorchQL avoids actually creating new tables. Instead, it stores, it performs a hash join because all of the joins we are supporting are basically equivalent to SQL equijoins. So what we do is under the hood, we essentially store hash values for the outputs of each function and just map those hash values together. Instead of what pandas does is it creates a new table every single time you need to actually create a join over a user-defined function.
Okay, thanks.
Other questions? Okay, I have one. I'm a big believer in domain-specific languages and how they can make things easier and make things work for a broader audience. So I'm curious about in your user study or maybe just in general the user group that you have in mind. Well, I guess to put it a little concretely, I noticed your operators are sort of database inspired, like join, right? So how familiar were your subjects in your study with these terms already, or what do you expect from your end user groups? And is this something that you have to worry about more, or is this pretty good shape already?
So that is a good question. So the users in our group were mostly graduate students, and so we didn't really ask them we just said that you need some familiarity with databases, but we didn't really ask them like how familiar they were, but they weren't like hardcore database engineers. In general, I would expect most computer scientists to be familiar with this because this is mostly like SQL style operations, except maybe things like reduce and the fact that there are user-defined functions. But then again, we should probably conduct some more thorough, rigorous one from a more ML audience perspective, because at the end of the day, it will be machine learning engineers who are working on this and not graduate students mostly.
Okay, thanks. We are right at time. Okay, thank you.
Right. Thank you.
Okay, are we ready? Yep, go ahead.
Hello, my name is Anan, and I'll present today our work verification of global robustness in neural networks. Okay, so neural networks are very successful but also prone to adversarial examples. Adversarial examples are small perturbations that if we add them to the input of the network, this can cause the network to change its decision. For example, consider this correctly classified sample of panda. If we add this very small noise, this can cause the network to change its decision from panda to gibbon. Okay, so to cope with adversarial examples, many works have suggested to use local robustness analyzers. In local robustness, we have an input, for example, this digit of 8. We take this input and define a set of noisy inputs around it, a neighborhood. We then take the neighborhood and show it to the analyzer. At the output of the analyzer, we have a set of outputs, each related to one of the inputs in the neighborhood. Now, if all the outputs are correctly classified to digit 8, we can say that the neighborhood is robust and there are no adversarial examples. Otherwise, we say that the neighborhood is not robust. Okay, so we explained how to analyze the robustness of this input of 8 digit. But let's say we want to analyze the robustness of other inputs of 8 digit, for example, this one. To do so, we take it, we define a neighborhood around it, we show the neighborhood to the analyzer and run the certification again. And now what if we want to analyze the robustness of all the 25 inputs here? We take each one of them, we show to the analyzer and run the certification again and again. But what if we want to analyze the robustness of cannot be obtained using local robustness, mainly because there are infinite number of feasible inputs of 8 digit. This actually brings us to global robustness. Now, global robustness aims to provide robustness guarantees over any input. To obtain this, prior works have employed different approaches. Some learn statistics defining some random distribution, for example, a Gaussian. They then sample inputs from this Gaussian to provide some global robustness guarantee. Others sample from the dataset itself until reaching some convergence criteria at which they can claim a global robustness guarantee. Others train autoencoders, learn some latent representation, and then define a robustness guarantee over this latent representation. Now, this approach can provide robustness guarantees to unseen inputs, but they cannot provide robustness guarantees to any input. This is because their guarantees are limited to a specific representation, either a specific distribution or dataset or latent representation. And this actually brings us to our goal. Our goal is to compute global robustness guarantees to any input. Now, typically, robustness guarantees are defined against an attack or perturbation. We define the perturbations by a function f representing the functionality of the perturbation, and by a perturbation range I epsilon. For example, let's consider the L infinity perturbation, where the perturbation function modifies each one of the pixels up to a change of epsilon. Now, in our work, we support a wide range of perturbations, for example, brightness, contrast, pitch, translation, and rotation. For these perturbations, we want to define a global robustness probability for any input. Okay, so to obtain global robustness for any input, we define a new global robustness probability. We call this probability delta global robustness. To understand our probability, let's consider this classifier. The classifier accepts a 2D input and classifies it into two classes, class 0 and class 1. Here in black, we show its decision boundaries. Now, before addressing global robustness, let's talk about local robustness. In local robustness, we typically pick inputs, we define a neighborhood around them, and given the perturbation, and then we check their robustness. For example, this red and green inputs. In global robustness, we want to define neighborhoods and check robustness over any input. But let's agree that no matter what we do, there will always be inputs that are close enough to the decision boundaries, and at them, the robustness probability won't hold. For example, this yellow input here. So to cope, we propose a new probability. Our probability says that we do not expect the network to change its classification if it's sufficiently confident in it. This means that if we are far enough from the decision boundaries, we do not expect the network to change its classification decision following some small perturbation. Okay, so we described our global robustness probability, and now let's define it. To define our delta global robustness probability, we build on a well-known concept of classification confidence. Now, in classification, we typically have an input x. We show this input to the classifier, and at the output, we have for each one of the classes a classification score. The classification confidence measures the difference between these scores. Say if x is classified as C tag, the classification confidence is the difference between the score of label C tag and the maximal score of the others. Now, to understand the classification confidence term, let's consider again the same 2D classifier we already saw in the last slide. We show here the classification confidence at axis Z. At the decision boundaries, the classification confidence is 0 because we cannot classify, and it is positive otherwise. Now using this term, we aim to define our delta global robustness probability. Okay, so using the classification confidence term, let's define now our global robustness probability. We say that given a perturbation function f and the range I for each x and for each possible perturbation epsilon type, if the confidence of the network in its classification is larger than delta, then the classification result of the clean input x is the same as the classification result of its noisy versions. To understand our delta, let's consider again the same 2D classifier. Here we focus on a small L infinity perturbation and highlight the non-robust inputs using colors. The z-axis still describes the classification confidence. Now for delta equals 0, our probability does not hold. This is because there are inputs with a classification confidence larger than 0 that are not robust. If we set delta to 9, our probability will hold. This is because all inputs with a classification confidence larger than 9 are robust to the perturbation. If we set delta to a very large value, for example delta equals 30, the probability also will hold, but by using it we will end up considering a lot of inputs to be not robust, although they are robust as we see here in the last figure. To that end, we say that the optimal delta is the minimal delta at which our probability holds. Okay, so we said that the optimal delta is the minimal delta at which our probability holds. So let's phrase our problem as a minimization problem. We want to find the minimal delta at which for each clean input classified as C-tag with a classification confidence larger than delta, its noisy inputs are also classified as C-tag. This problem cannot be solved using standard optimization tools, mainly because we have the for-all operator and the implies operator. And to cope, we define a new problem aiming to find the maximal delta at which we still can find a clean input classified as C-tag, but its noisy version classified to other label. We replaced the for-all operator with the exist operator and the implies operator with the AND operator. This means that instead of finding the minimal globally robust bound, we find the maximal globally non-robust bound. In our paper, we have a lemma showing that the solution of problem 2 plus a very small number is actually the solution of problem 1. For example, let's consider again the 2D classifier from previous slides. If we had then delta equal 9 as the minimal globally robust bound solving problem 1, then delta equal 8.9999 is the maximal globally non-robust bound solving problem 2. By adding a small number to it, we will eventually achieve the solution of problem 1. Okay, so now we have this maximization problem that we can solve using standard optimization tools. However, the main challenge to solve this problem is its highly nonlinear constraints. Remember that the classification confidences are output of the networks, and the network itself is highly nonlinear entity. And we actually have two confidences, one over the clean version and one over the noisy version. So to cope with that, we depend on mixed integer programming, MIB. MIB actually encodes the neurons in the network using booleans and continuous variables. So eventually, using the MIB encoding, we can represent the network by linear constraints and boolean variables. However, the problem is that the complexity of MIB is exponential with the number of booleans. And our probability doubles the number of booleans, since we have two networks, one accepting the clean input and one accepting its noisy version. So to solve our optimization problem efficiently, we should reduce this complexity. To reduce the MIB encoding complexity, we suggest three techniques. First, we suggest to depend on anytime optimization. Instead of going after the precise solution in one shot, we compute it by tracking and refining upper and lower bounds, bounding that precise solution. As we can see in the first figure here, the blue line is the upper bound and the red line is the lower bound, and they get refined with time progress. Although we can see that the bounds are refined with the time progress, the anytime optimization alone is not enough. This is because even after 10 minutes, we still do not converge to the optimal global robustness bound. Because of that, we suggest additional techniques. The second technique is encoding dependencies between the MIB parameters of the two copies. Remember that we have two copies, one accepting the clean input and one accepting its noisy version. By leveraging the dependencies between these copies, we converge to the precise global robustness bound after 200 seconds, as we can see in the middle figure. We call the last technique hyper-adversarial attack. In this technique, we try to find suboptimal solutions and encode them to boost the optimization solution. In the last figure, we show that it speeds up the solution, and now we converge to the precise solution within 70 seconds. Okay, so let's describe our dependencies encoding. The main goal of dependencies encoding is to reduce the number of booleans and improve the optimization search space. As we said, we aim to impose linear constraints between the parameters of the network accepting the clean input and the network accepting its noisy version. To illustrate, let's consider the following example. We focus here on 4x4 input and run a collision attack which makes the first pixel black. The upper branch considers the clean input and the lower branch considers its noisy version, where we set the value of the first pixel to 0. Okay, so let's focus now on the orange rectangle here. The upper orange rectangle passes the convolutional layer. The lower orange rectangle with the 0 values as at its first pixel also passes the same convolutional layer. Because of that, we can say that the upper convolutional result is always larger than the lower convolutional result. This is because in the upper version we have positive number multiplied by 1, and in the lower version we have 0 multiplied by 1. As a result, we can encode this inequality dependencies between the parameters of the upper version and the lower version. We run similar computations for the rest of the neurons, like the green neuron, red, and the blue neurons. Also for the neurons in the second layer. Eventually, we removed 3 booleans because of the equality dependencies and added a lot of inequalities, pruning the optimization search space. Okay, so let's describe our hyper-adversarial attack. Remember that our ultimate goal is to compute delta globally robust bound for any input. However, the computational complexity to obtain this is high. So instead of finding bound for any input, we focus on M inputs on M inputs only. For the M inputs, we solve the following optimization problem to obtain inputs with maximal classification confidence. At them, the noisy versions are misclassified. To understand that, let's consider the following example. Here we have 6 inputs. Each has different confidence. For example, the first has 1 and the sixth have 6. We run the optimization process. And at the output, we have solutions such that they have maximal confidences and their corresponding noisy inputs are misclassified. Here we show how the optimization solutions converge. For example, the classification confidence of input 1 starts from 1, increases until converging to confidence 2, which is a valid solution. This is because its clean input confidence is maximal and its noisy version is misclassified. Now, note that the bound that we found by our attack is suboptimal to the globally robust bound, since it was computed using only 6 inputs and not using any input. Still, by submitting it to the optimizer as a lower bound, we prune the optimization search space. Okay, so now let's describe Vega, our full system. Vega accepts as an input a classifier D, a class C tag, a target class CT, a perturbation function, and a perturbation range. We encode 2 networks, one for the clean input and one for its noisy version. We then compute and encode the dependencies. In parallel, we run our hyper-adversarial attack. We pass all of that to the MIP solver and define our maximization problem. Before we submit the upper and lower bounds of the maximization solution, we add a small number to them. At the output, we have lower and upper bounds bounding the minimal globally robust bound. Okay, Vega comes with formal guarantees. First, it is sound. Second, it always returns upper and lower bounds, bounding the precise minimal globally robust bound. Okay, so now let's describe our evaluation. We evaluate Vega over the data sets MNIST, Fission MNIST, and CFAR10. We compare Vega to 4 baselines, random sampling, dataset sampling, and a precise verifier called Marubo, also a version of MIP-only verifier. As we can see here, the sampling approach can compute only a lower bound. The precise approach compute both lower and upper bounds, but their bounds are not tight. We can see that Marubo and the MIP-only version have big gaps between their lower and upper bounds. But Vega closes this gap. Our results show that Vega provides 82 times tighter bounds than Marubo and 18 tighter lower bounds than sampling approach. Also, it is faster than Marubo by 130 times, but as expected, it is slower than the sampling approach. And here we can show other examples of different perturbations. Okay, so now let's see what insights into network global robustness can be obtained by Vega. We show here heat maps, each providing the minimal global robust bounds for all possible transitions. For example, by the red arrow, we show the transition from class 0 to class 1 and its minimal globally robust bound, which is 4. This means that any input which is classified as 0 with confidence larger than 4 cannot be misclassified to level 1 by this perturbation. Using this, the designer of the network can understand the real global robustness level of the network, and the attacker can understand where the attacks are feasible and where they are not. Okay, so now let's conclude. We address the problem of computing global robustness guarantees in neural networks. We introduce our concept called delta global robustness. We propose Vega, our approach to compute the minimal delta global robustness bound. Vega employs constraint optimization, encodes dependencies and optimization hands to boost its computations. It is tighter by 82 times and faster by 130 times compared to Morobo. It is tighter by 18 times compared to the sampling approach. And it provides insights into networks' global robustness. Okay, thank you for your attention and questions.
Are we live for questions? Okay, there's no Q&A. All right, if you have a question, you can ask me. I will not know the answer. But you can ask me and we'll get it passed on. Thank you, everyone. Enjoy the reception.